the duck-rabbit problem. Let us begin with a simple, elegant puzzle, a drawing composed of just a few lines that holds within it a profound secret about the nature of perception. You may have seen it before. It is the duck-rabbit, an ambiguous image first popularized by psychologist Joseph Jastrow. At first glance you see a duck, its bill pointing to the left. It is unmistakable. The curve forms its head, the dot its eye, the two lines its beak. You see a duck. But then, with a subtle shift in your mind, a cognitive flicker, the entire image reorganizes itself. The beak that pointed left now becomes the ears of a rabbit pointing right. The back of the duck's head is now the rabbit's face. The image on the page has not changed by a single pixel, yet the reality you perceive has completely transformed. In one moment, a duck. In the next, a rabbit. You can hold one, then the other, but you cannot consciously perceive both simultaneously. This simple illusion is not a mere party trick. It is a powerful demonstration of one of the deepest secrets of perception. Your brain is not a passive receiver of information, but an active, dynamic interpreter, a hypothesis tester constantly striving to impose meaningful order on sensory data. The duck-rabbit problem reveals that what you see is not just what is there, but what your brain decides is there. The mechanism at play here is a beautiful dance between two fundamental modes of processing. The first is bottom-up processing. This is the flow of information from the external world inward. Your eye's retinas register the raw sensory data, the lines, the curves, the single dot, their specific arrangement and orientation on the page. This is the raw, meaningless input, the physical reality of the stimulus. If perception were only a bottom-up process, we might just see a collection of abstract lines, a meaningless doodle. But that is not what we experience. The magic happens with the engagement of top-down processing. This is the flow of information from your mind's pre-existing knowledge, your concepts, memories and expectations, downwards to interpret the sensory data. Your brain, having seen ducks and rabbits before, possesses conceptual templates for both. When it receives the ambiguous data from the lines, it actively tries to fit it to one of these templates. It forms a perceptual hypothesis. Perhaps this data represents a duck. It then tests this hypothesis against the incoming lines. The lines fit the duck template remarkably well. The hypothesis is confirmed and voila, you consciously perceive a duck. The raw data has been organized into a meaningful whole. But the ambiguity of the image allows for an alternative, equally valid hypothesis. Perhaps this data represents a rabbit. A slight shift in attention, perhaps a random fluctuation in neural activity, or a conscious effort to see it differently, can cause the brain to switch hypotheses. It drops the duck template and applies the rabbit template. The data fits this new hypothesis just as well. The beak becomes ears, the head becomes a face, and your perceived reality flips. The raw bottom-up data has remained constant, but the top-down interpretation has changed, and with it, your entire conscious experience of the image. The reason you cannot see both simultaneously is because your brain, in its quest for coherence, cannot hold two contradictory perceptual hypotheses for the same patch of sensory data at the same time. It must commit to one meaningful interpretation. The flipping between the two states is your brain rapidly abandoning one stable interpretation for another. This phenomenon is known as bistable perception. It reveals the brain's decision-making process in action. Perception is not a passive reflection but an active judgment. This principle extends far beyond simple line drawings. It is a fundamental aspect of how we navigate our entire world. We constantly encounter ambiguous social cues, unclear sounds, or complex visual scenes. Our brain uses top-down processing to resolve this ambiguity based on context, expectation, and past experience. When you hear a garbled word in a sentence, your brain often fills in the correct word based on the sentence's meaning. When you see a friend's ambiguous facial expression, you interpret it as playful or annoyed based on your expectation of their mood. We are constantly making best guesses about reality, and our conscious perception is the result of those guesses. The duck-rabbit problem is therefore a profound philosophical tool, used famously by Ludwig Wittgenstein to explore the nature of seeing and interpretation. It demonstrates that seeing is not the same as seeing as. We don't just see lines, we see them as a duck or as a rabbit. This act of seeing as is a conceptual, interpretive act, not a purely sensory one. It suggests that our experience of the world is always mediated by our concepts, our language, our history. Two people can look at the exact same data. Whether it's an ambiguous image, a complex social event, or a political issue, and by applying different top-down frameworks, can come to perceive two entirely different realities. Their disagreement is not about the raw data, but about the interpretive framework used to make sense of it. This understanding can be a source of profound intellectual humility and psychological peace. It reminds us that our perception of the world is not an absolute truth, but a constructed interpretation, a hypothesis. It allows for the possibility that other interpretations may be equally valid from a different perspective. It opens up space for curiosity about how others see the world, rather than asserting the absolute authority of our own perception. As you continue to relax deeply, let the image of the duck-rabbit gently float in your mind. See the duck. Now let it become the rabbit. Feel the effortless yet profound shift in your perceived reality. Acknowledge this as the silent, powerful work of your own mind, actively creating meaning from ambiguity. Recognize that this process is happening all the time, in every moment of perception. The world you experience is a partnership between the external data and your internal interpretation. Find peace in this creative dance. Let go of the need for your perception to be a perfect, rigid reflection of reality. Instead, appreciate it as a dynamic, flexible, and deeply personal construction. Resting calmly in the knowledge that your brain is not just a camera, but a masterful and constant artist, shaping the very world you inhabit. Gestalt principles of perception. Having seen how the brain imposes meaning on ambiguous stimuli, let us now explore some of the fundamental rules, or organizing principles it uses to structure the sensory world in the first place. How does your brain take a chaotic flood of visual information, millions of points of light, color, and shade, and effortlessly group it into coherent objects, distinct from the background? This automatic, unconscious process is guided by a set of heuristics known as the Gestalt principles of perception. The term Gestalt is German for form or whole, and the core idea of Gestalt psychology is that the human mind perceives the whole as being other than or different from the sum of its parts. Our perception is not built up from tiny individual sensations, but is primally organized into meaningful wholes according to these innate principles. These principles are the secret grammar of our visual system, the silent laws that allow your brain to create a coherent reality from sensory chaos. Understanding them is to understand the very architecture of how you see. Let's begin with the principle of proximity. This principle states that objects or elements that are close to one another in space or time are perceived as belonging together, as forming a group. Imagine a scattering of 100 dots on a page. If they are randomly distributed, you see a field of dots. But if you arrange them so that clusters of dots are close together, separated by larger empty spaces, you will no longer see 100 individual dots. You will automatically, without any conscious effort, perceive distinct groups of dots. Your brain uses nearness as a powerful cue for grouping. This happens everywhere in our daily perception. We perceive people standing close together at a party as a single conversation group. We read words as unified objects because the letters are in close proximity, separated by spaces from other words. This principle is a fundamental heuristic. Things that are near each other in the world are often related, so the brain makes an efficient bet that they belong together. It's a simple rule that dramatically simplifies the visual scene, reducing cognitive load. Next, consider the principle of similarity. This principle states that our minds tend to group together elements that are similar in some way, be it by color, shape, size, or orientation. Imagine again a field of dots, but this time half are red and half are blue, all intermingled. You will not see a random mix. Your visual system will effortlessly group the red dots together and the blue dots together, perceiving distinct red groups and blue groups even if they are not spatially close. A column of squares placed next to a column of circles will be seen as two distinct columns, not a series of rows. We use this principle constantly. We perceive a sports team as a unified group because they all wear the same color jersey. We group different types of plants in a garden based on their similar shapes or colors. Similarity, like proximity, is a powerful shortcut for organizing the world. It allows the brain to quickly categorize and parse complex scenes, identifying patterns and relationships based on shared features. Now let us explore the principle of closure. Our minds have a powerful tendency to perceive incomplete or fragmented figures as complete, whole objects. We automatically fill in the gaps to create a unified shape. The famous logo for the World Wildlife Fund uses this principle. It depicts patches of black arranged in such a way that we perceive a complete panda, even though the lines defining the panda's back and head are not actually drawn. our brain completes the figure. Similarly, if you see a circle with a small section missing, you are more likely to perceive it as a broken circle, rather than just a complex curved line. The mind seeks wholeness and coherence, actively filling in missing information to create a simpler, more stable percept. This drive for closure is what allows us to recognize objects that are partially occluded or hidden from view. We see a car partially blocked by a tree and perceive the whole car, as our brain fills in the hidden parts based on the visible information and our prior knowledge of what cars look like. This is a highly adaptive skill, allowing us to build a complete model of our environment from incomplete sensory data. Another related principle is continuity, or good continuation. This states that our perception tends to favor smooth, continuous lines or patterns over abrupt, disjointed ones. When two lines intersect, we tend to perceive them as two single, unbroken lines crossing each other, rather than as two V-shapes touching at the point. Our brain assumes that lines flow smoothly. This principle helps us follow the trajectory of an object in motion or trace the path of a winding road, perceiving a single continuous entity rather than a series of disconnected segments. It reflects the brain's assumption that the world is generally smooth and ordered, and it organizes perception accordingly to reflect this underlying assumption. Finally, the principle of figure-ground perception is perhaps the most fundamental of all. This describes our innate ability to distinguish an object, the figure, from its surrounding background, the ground. The figure seems more object-like, more memorable, and appears to be in front of the ground. The duck-rabbit illusion we just explored is also a classic example of figure-ground reversal, where what counts as figure and what counts as ground can flip. In the Rubens vase illusion, you can see either two faces in profile, the figures, against a white background, or a white vase, the figure, against a black background. Your brain organizes the scene into a figure and a ground, but which can be ambiguous, highlighting the active, interpretive nature of this process. This ability to parse the world into objects and backgrounds is essential for navigating our environment and recognizing things within it. These Gestalt principles are not conscious strategies. They are automatic, pre-attentive rules hardwired into our perceptual system. They demonstrate, with beautiful clarity, how your brain creates reality. It doesn't just passively register sensory data. It actively structures, organizes, and simplifies that data into a world of coherent objects, groups, and patterns. These principles are the mind's secret grammar for seeing, the invisible architecture that builds a meaningful world out of a chaotic sea of sensation. They are a profound example of how our experience is not a direct reflection of the world, but a highly structured interpretation of it, optimized for efficiency and meaning. As you continue to relax deeply, become aware of the wholeness of your sensory experience. The way disparate sounds merge into the single experience of a room's ambience. The way the sensations of the surface beneath you form the unified feeling of rest. This is the Gestalt process at work, your mind silently and effortlessly creating coherence. Acknowledge this silent, organizing intelligence within you. Appreciate the elegance of these principles, proximity, similarity, closure, continuity, figure ground, as the fundamental tools your brain uses to build a meaningful reality for you to inhabit. Find peace in this effortless coherence, letting go of the need to analyze the parts, and simply resting within the gentle, unified whole of your present experience as you drift towards sleep. Change blindness. We generally operate under the assumption that we have a rich, detailed, and continuous visual experience of the world around us. We feel as though we are taking in the entire scene before our eyes, like a high-resolution camera constantly recording every detail. But what if this feeling of a complete, detailed picture is itself a profound illusion? What if we are, in fact, remarkably oblivious to significant, even dramatic, changes happening right in front of our eyes, as long as those changes occur during a brief disruption in our visual input? This startling phenomenon, our surprisingly poor ability to detect obvious changes in a visual scene, is known as change blindness. It is a powerful secret of perception that shatters the myth of a perfect photographic visual memory and reveals that our brains do not build a detailed, pixel-by-pixel model of the world. Instead, we seem to perceive the world on a just-in-time basis, focusing only on the gist of the scene and the specific details relevant to our current task, while remaining blind to much of the rest. This psychology mystery forces us to question the very nature of seeing and attention, revealing that our perceived reality is far more sparse and constructed than our subjective experience leads us to believe, inviting deep relaxation through accepting the limits of our own awareness as you fall asleep. The classic demonstration of change blindness often involves a flicker paradigm experiment. Participants are shown two versions of the same image, which are alternated back and forth with a brief blank screen or a visual disruption, like a mud splash, appearing between them. The two images are identical except for one significant change. A person's shirt might change color, a large building might disappear from the background, or an airplane's engine might vanish. Our intuition tells us such a large change should be immediately obvious. Yet, participants often stare at the flickering images for a remarkably long time, sometimes for a minute or more before they are able to spot the change. The brief visual disruption prevents our automatic motion detection systems from immediately drawing our attention to the location of the change. Without that automatic cue, we are forced to engage in a slow, deliberate serial search of the scene, element by element, to find the discrepancy. This reveals that we were not holding a detailed snapshot of the first image in our minds to compare with the second. If we were, the change would be instantly apparent. This phenomenon isn't just a laboratory curiosity, it happens constantly in our everyday lives. Researchers have conducted real-world studies with astonishing results. In one famous experiment, a participant is giving directions to a stranger, who is actually an experimenter. During the conversation, two other experimenters carrying a large door walk between them, briefly occluding their view of each other. During this brief moment, the original stranger is replaced by a different person, a different height with different clothes and a different voice. A shocking number of participants, around half, failed to notice this dramatic swap. They simply continue giving directions to the new person as if nothing happened. Their brain, focused on the task of giving directions, has encoded only the gist of the person, a man asking for directions, and failed to encode the specific details that would have revealed the change. This is change blindness in the wild. We don't see what we are not paying attention to, even when it's as obvious as the person we are talking to being replaced. So, why are we so susceptible to change blindness? It seems to stem from the fundamental way our visual system is designed to operate, prioritizing efficiency over exhaustive detail. Creating and maintaining a highly detailed real-time representation of our entire visual field would be computationally immense and incredibly wasteful for the brain. Most of the information in our visual field is redundant or irrelevant to our current goals. Instead of building a detailed internal photograph, our perceptual system seems to operate on a more efficient model. It uses quick eye movements, called saccades, to scan the environment, but only fully processes the information at the center of our gaze in the fovea, where visual acuity is highest. We get the gist, or overall meaning of the scene very quickly, and then our attention is directed only to objects or areas that are relevant to our current task or goal. The feeling that we see the whole scene in detail is itself a construction. Our brain creates this illusion of a complete, rich visual world by combining the high-resolution information from our foveal vision with the less detailed peripheral information and our own internal models and expectations of what the world should look like. We assume the details are stable and don't need to be constantly re-encoded. We operate under the assumption of continuity. Change blindness occurs when this assumption is violated in a way that our attentional system isn't prepared for. The brief visual disruption, the flicker, the door, prevents the automatic motion detection cues that would normally capture our attention, leaving us reliant on our sparse internal representation, which lacks the detail needed to spot the change. We are essentially blind to anything we have not allocated focused attention to. This has profound implications for our understanding of perception, consciousness, and memory. It suggests that our visual consciousness is not a continuous stream of detailed information, but rather a series of focused spotlights of attention cast upon a very sparse internal model of the world. The richness and detail we feel we experience is a grand illusion, a story our brain tells us based on a combination of minimal sensory input and vast amounts of stored knowledge and expectation. It also demonstrates the incredibly tight link between attention and perception. We do not simply see what is out there, we see what our attention selects for processing. Without attention, even a dramatic change can remain effectively invisible. This psychology mystery also raises important practical concerns, particularly regarding eyewitness testimony and driving safety. An eyewitness might be absolutely confident they saw an event clearly, yet change blindness research suggests they likely missed crucial details to which they were not paying direct attention. A driver focused on the car ahead might completely fail to notice a pedestrian stepping into the road from the periphery until it's too late. Recognizing our inherent limitations and detecting change is crucial for fostering humility about the reliability of our own visual experience and for designing safer systems. Contemplating change blindness is a deeply humbling experience. It forces us to confront the fact that our subjective sense of a rich, stable visual reality is a clever construction, a user interface generated by our brain for efficient interaction with the world. The real processing is happening behind the scenes, and it's far more selective and sparse than we intuitively believe. As you continue to relax deeply, allow your visual field, even behind closed eyes, to soften. Acknowledge that your feeling of seeing a complete, detailed world is a beautiful creation of your mind, a seamless illusion woven from fragments of attention and vast reservoirs of expectation. Let go of the need to be a perfect observer, to see and remember everything. Recognize that your brain, in its wisdom, prioritizes meaning and function over exhaustive detail. Find peace in this cognitive efficiency. Appreciate the secret of perception that you experience, not a photograph, but a story crafted by your brain to make the world navigable. Resting calmly, released from the burden of perfect awareness, within the sparse and beautifully constructed reality of your mind. Inattentional blindness. Continuing our exploration into the profound limits of our perception, let us now focus on a closely related, yet distinct and equally startling phenomenon: inattentional blindness. While change blindness reveals our failure to notice changes in a scene, inattentional blindness demonstrates something even more shocking: our failure to notice a fully visible but unexpected object when our attention is deeply engaged in another task. We can be looking directly at something, and yet, if our attention is directed elsewhere, we can fail to see it at all. It remains invisible to our conscious awareness. The most famous demonstration of this is the invisible gorilla experiment, a powerful psychology mystery that serves as a stark metaphor for the selective nature of human attention and perception. It reveals that seeing is not a passive act of receiving light, but an active process of attentional filtering. What we consciously perceive is not what is in our visual field, but what our brain chooses to process. This profound secret of perception forces us to question the reliability of our own awareness and the very meaning of seeing. The original experiment, conducted by Daniel Simons and Christopher Chabris, is elegant in its simplicity and devastating in its results. Participants are asked to watch a short video of two teams of people, one team in white shirts and one in black shirts, passing basketballs back and forth. Their task is specific and demanding: to count the number of passes made by the team in white shirts. They are instructed to focus intently on this task. About halfway through the video, a person in a full gorilla costume walks slowly into the middle of the scene, stops, thumps their chest, and then walks off. The entire event lasts about 9 seconds and is fully visible. After the video, participants are asked for their pass count. Then comes the crucial question: did you notice anything unusual in the video? A remarkable number of participants, roughly 50% in the original studies, report seeing nothing out of the ordinary. They are completely oblivious to the gorilla. They did not see it. When the video is replayed without the counting task, they are often shocked, amazed, and sometimes disbelieving that they could have missed something so obvious and bizarre. This is inattentional blindness. The phenomenon occurs because attention is a limited resource. Our brains cannot consciously process every single piece of sensory information bombarding us at any given moment. To function, we must selectively allocate our attentional resources to what is most relevant to our current goals. In the experiment, the task of counting passes requires significant attentional focus. The brain dedicates its resources to tracking the white shirt players, the ball, and the act of passing. It actively filters out information deemed irrelevant to this task, including the black shirt players, and, astonishingly, the unexpected gorilla. The gorilla's visual information undoubtedly enters the eyes and is processed at some basic level in the visual cortex, but it is not selected by the attentional spotlight for entry into conscious awareness. Without the benefit of focused attention, the gorilla remains functionally invisible. This is a profound mindfuck. It's not that the participants' eyesight was poor, or that the gorilla was transparent. They were often looking directly at the area where the gorilla appeared. Their failure was not one of sensation, but of perception and attention. It demonstrates that there is a critical distinction between looking and seeing. Looking is the physical act of directing one's gaze. Seeing is the conscious experience that results from attentional processing. The experiment proves that one can look directly at something without seeing it, a finding that radically contradicts our intuitive sense of awareness. Like change blindness, inattentional blindness has significant real-world implications. It helps explain many accidents where people report, "I was looking, but I just didn't see them." A car driver focused on looking for other cars at an intersection might fail to see an unexpected motorcycle or cyclist, even if they are directly in their line of sight, because their attentional filter is set for car-sized objects. Radiologists tasked with meticulously scanning medical images for anomalies have been shown to fail to notice an image of a gorilla superimposed on a lung scan if they are not explicitly looking for such an absurdity. Their attention is so finely tuned to finding signs of disease that the unexpected, obvious anomaly is filtered out. The phenomenon highlights the dangers of divided attention, such as texting while walking or driving, as our engagement in one task can render us blind to critical hazards in our environment. Philosophically, inattentional blindness deepens the mystery of how the brain creates reality. It reinforces the idea that our conscious experience is not a comprehensive, wide-angle view of the world, but a highly edited, task-relevant sliver of it. Our brain presents us with what it thinks we need to know for our current goal, and discards the rest, creating a seamless but ultimately incomplete user interface for our consciousness. It questions our claims to be good observers. Even when we believe we are paying close attention, our focus is narrower than we think, and we are surrounded by a world of invisible gorillas, unexpected events and objects to which we are blind. What factors influence inattentional blindness? The difficulty of the primary task is one. The more attention a task demands, the more likely we are to miss unexpected stimuli. The degree of similarity between the unexpected object and the attended objects also matters. We are more likely to notice an unexpected white object than a black one in the gorilla experiment. Our own expectations also play a key role. We don't expect to see a gorilla in a basketball game, so our brains are not primed to detect it. This links to the powerful role of top-down processing in shaping perception. Our expectations guide what we see. Contemplating inattentional blindness is a powerful exercise in intellectual humility. It serves as a stark reminder of the inherent limitations of our own awareness. It encourages a more cautious and less confident approach to our own observations and memories, especially in situations demanding high attention. As you continue to relax deeply, allow your field of awareness to soften and expand. Acknowledge the focused beam of your attention, and consider the vast world of sensory information that lies just outside that beam, in the periphery of your consciousness. Picture the invisible gorilla, walking unseen through a scene of focused activity. Recognize that your own conscious experience is a similarly filtered reality, constructed by the powerful, selective, and limited nature of your attention. Let go of the illusion that you see everything. Find peace in the efficiency of your mind's filtering system, even as you acknowledge its startling blind spots. This is not a flaw, but a fundamental secret of perception. Resting calmly, knowing that your brain is constantly making choices about what becomes part of your experienced world, gently editing reality to help you navigate. Synesthesia. Let us now explore a phenomenon that beautifully and radically dismantles our ordinary assumptions about the separation of the senses. For most of us, our sensory experience of the world is neatly compartmentalized. Vision sees, hearing hears, taste tastes. These channels seem distinct and independent. But imagine a world where this is not the case. Imagine hearing a piece of music and simultaneously seeing a vibrant cascade of colors projected in your mind's eye. Imagine looking at the black and white letter, and experiencing it as inherently vividly red. Or imagine tasting a flavor and feeling a distinct geometric shape on your fingertips. This extraordinary blending of sensory or cognitive pathways is known as synesthesia. It is not a metaphor nor a flight of fancy, but a genuine neurological trait where the stimulation of one sense automatically and involuntarily triggers an experience in a second, unrelated sense. Synesthesia is a breathtaking psychology mystery, a union of the senses that offers us a rare glimpse into the diverse ways the brain can create reality, questioning the very idea of a universal, uniform perceptual experience and inviting us to fall asleep contemplating the beautiful, cross-wired symphony of the mind. The word synesthesia comes from the ancient Greek, meaning to perceive together. It is a condition characterized by several key features. The synesthetic experiences are involuntary, they happen automatically without conscious effort. They are consistent over time. If the number 7 is lime green for a synesthete today, it will be lime green for them decades later. The pairings are also highly idiosyncratic. While one synesthete might experience A as red, another might experience it as blue, and a third might not have color-letter associations at all. Finally, the experiences are often perceptually real and vivid for the individual, not just imaginative associations. The experience isn't like seeing red. For some, the color is literally projected into their visual space. There are many different forms of synesthesia, potentially as many as there are possible pairings of senses and concepts. Grapheme color synesthesia, the association of letters or numbers with specific colors, is one of the most studied and common forms. Chromesthesia, where sounds, music, voices, environmental noises evoke colors, is also prevalent and has been reported by many famous musicians, including Duke Ellington and Pharrell Williams, who use their synesthetic colors as part of their creative process. Lexical gustatory synesthesia is a rarer form where spoken or written words trigger distinct taste or texture sensations. A person with this form might report that the name Derek tastes like earwax, a famously documented case. Mirror touch synesthesia is a particularly empathetic form where an individual feels a tactile sensation on their own body when they see someone else being touched. Spatial sequence synesthesia involves perceiving sequences like numbers, days of the week, or months of the year as occupying specific, consistent locations in the space around them, forming a kind of mental 3D calendar. So, what causes this remarkable blending of the senses? The exact neurological mechanisms are still a subject of intense research, making it a key psychology mystery, but the leading hypothesis points to atypical brain connectivity. One theory, known as the cross-activation hypothesis, suggests that in synesthetes, there is an excess of neural connections, or a failure of normal inhibition, between adjacent brain regions that process different types of sensory information. For example, the brain area responsible for identifying letter shapes is located right next to the area responsible for processing color, area V4. The theory posits that in grapheme color synesthetes, there is a degree of crosstalk or activation leakage between these two areas. When the letter recognition area is activated, it automatically co-activates the color processing area, triggering the subjective experience of color. This might be due to genetic factors that influence neural development, perhaps resulting in less pruning of the more interconnected neural pathways that are common in early infancy. Synesthesia does tend to run in families, lending support to a genetic basis. Another related idea is the disinhibited feedback hypothesis. This theory suggests that the cross-modal connections exist in all human brains to some extent, but are normally kept in check by inhibitory processes. In synesthetes, this inhibitory feedback might be weaker, allowing signals from different sensory processing streams to consciously blend. This might explain why synesthetic-like experiences can sometimes be temporarily induced in non-synesthetes through meditation, sensory deprivation, or the use of psychedelic substances, which are known to alter patterns of brain connectivity and inhibition. Studying synesthesia is profoundly important because it provides a unique window into the secrets of perception and consciousness. It powerfully demonstrates that our individual subjective experience of reality is not a direct copy of the external world, but a construction of the brain. The fact that the same black and white letter can be experienced so differently by different brains highlights the constructed nature of qualia, the subjective qualities of experience. It questions any naive realist assumption that we all perceive the world in the same way. It is a living, breathing example of the brain's role in creating, not just recording, our perceptual reality. Furthermore, synesthesia offers valuable clues about cognition more broadly. Many synesthetes report that their unusual sensory pairings act as powerful mnemonic devices, aiding their memory. The link between synesthesia and enhanced creativity is also an area of active research. Does the cross-wiring of concepts and senses facilitate novel metaphorical thinking and artistic expression? By studying these unique brains, we can learn more about how all our brains process information, form concepts, and create the rich, multisensory world we inhabit. The mystery of synesthesia is the mystery of individual difference at its most fundamental level, the level of raw perception. It forces us to ask, what other ways of experiencing reality are possible? Is our typical, compartmentalized sensory experience just one configuration among many? What would it be like to taste shapes or hear colors? The existence of synesthesia opens a door to imagining a vast spectrum of possible conscious experiences. As you continue to relax deeply, allow your senses to soften and expand. Imagine for a moment that the boundaries between them could blur. What color would the sound of this voice be? What taste would the feeling of relaxation have? Contemplate the intricate hidden wiring of your own brain, the silent processes that weave light, sound, and touch into your coherent reality. Acknowledge the beautiful mystery of synesthesia as a testament to the brain's creative diversity. Find peace in knowing that the way you perceive the world is uniquely yours, a private symphony orchestrated by your brain, and that other symphonies with different blended instruments are equally possible. Resting calmly within the rich, multisensory tapestry of your own personal existence. Optical Illusions explained. Let us now journey into a realm where our sense of sight, our most trusted guide to the external world, is playfully and profoundly deceived. We explore the world of optical illusions. These are images that fool the eye and the brain, causing us to perceive something that is demonstrably different from objective reality. A line that appears longer than another, parallel lines that seem to curve, static images that appear to move. These are not flaws in our vision, but rather fascinating windows into the hidden workings of our perceptual system. Optical illusions are not mere curiosities. They are powerful psychological tools that reveal the unconscious assumptions, the predictive models, and the interpretive shortcuts your brain uses to create reality. By understanding why we are fooled, we uncover the deep secrets of perception itself. The fact that our minds can be so consistently and predictably misled questions the very idea of direct, unmediated sight, inviting deep relaxation through the calm observation of your brain's own clever, and sometimes mistaken, creative processes as you fall asleep. Let's begin with one of the most famous and powerful geometric illusions, the Muller-Lyer illusion. Imagine two straight lines of identical length. On the ends of the first line, we draw arrowheads pointing inwards like this. On the ends of the second line, we draw arrowheads pointing outwards like fins on a fish like this. Almost everyone who sees this will perceive the second line, the one with the fins pointing outwards, as being significantly longer than the first line with the inward pointing arrows. Yet, if you were to take a ruler to the screen, you would find that the central horizontal lines are exactly the same length. Why does this simple addition of fins so dramatically warp our perception of length? One of the most compelling explanations for the Muller-Lyer illusion is the carpentered world hypothesis, proposed by psychologist Richard Gregory. This theory suggests that our brains, having evolved and developed in environments filled with straight lines and right angles, buildings, rooms, furniture, have learned to interpret certain two-dimensional cues as representations of three-dimensional space. The inward-pointing arrows resemble the near corner of a room or building projecting towards us. The outward-pointing fins resemble the far corner of a room receding away from us. Our brain automatically, unconsciously applies the rules of size constancy, which we will explore later. It knows that an object further away must be larger to cast the same size image on our retina. So, it interprets the line with the far corner fins as being further away and therefore perceptually scales it up, making it appear longer. The line with the near corner arrows is perceived as closer and is scaled down. The illusion is a byproduct of a normally useful 3D interpretation mechanism being misapplied to a flat 2D image. People from cultures with fewer carpentered right-angled environments have been shown to be less susceptible to this illusion, lending support to the idea that it is, at least in part, learned from our visual environment. Now, let us consider the Ponzo illusion. Imagine two identical horizontal lines placed between two converging vertical lines, like railway tracks receding into the distance. The horizontal line that is placed higher up in the image, where the tracks appear closer together, will seem significantly longer than the identical line placed lower down. Again, a ruler would confirm they are the same length. The explanation is similar to Muller-Lyer's, relying on the brain's use of depth perception cues. The converging lines create a powerful sense of linear perspective, telling our brain that the top of the image is further away than the bottom. Since the two horizontal lines cast retinal images of the same size, the brain's size constancy mechanism concludes that the one that appears further away must be objectively larger in reality. It scales up our perception of the top line, creating the illusion. Your brain is not seeing two lines on a flat surface. It is actively trying to construct a logical 3D scene, and in doing so, it distorts the perception of size to maintain consistency with the perceived depth. There are many other types of illusions that reveal different secrets of perception. Illusions of contrast, like the checker shadow illusion, demonstrate how our brain adjusts our perception of color and brightness based on surrounding context. In this illusion, two checkerboard squares of the exact same shade of gray appear as dramatically different colors, one light, one dark, because one is perceived to be in a shadow. Your brain doesn't just register the raw light value, it calculates and presents to you a perception of the square's true surface color by subtracting the effect of the shadow. It's trying to show you the constant property of the object, not the transient quality of the light hitting your eye. Illusions of motion, like the peripheral drift illusion or certain psychedelic aerostatic images that seem to shimmer and move, exploit the way our motion-detecting neurons interact. Subtle differences in luminance, contrast, and the arrangement of shapes can trigger these neurons in a way that creates a false signal of movement, especially in our peripheral vision. Your brain is so attuned to detecting motion for survival that these arrangements can trick the system into firing. What all these optical illusions have in common is that they are not simply mistakes. They are logical consequences of the way our perceptual system works. They reveal the powerful, unconscious inferences and assumptions your brain constantly makes to transform ambiguous, two-dimensional retinal information into a stable, coherent, three-dimensional world. It assumes that lines continue, that shadows darken surfaces, that objects further away appear smaller. These assumptions are incredibly effective and accurate almost all of the time in the real world. Illusions are simply special cases where the visual input is carefully crafted to exploit these assumptions, causing the system to arrive at a perceptually incorrect, but logically consistent conclusion based on its built-in rules. Contemplating these illusions is a deeply humbling experience. It's a direct, personal demonstration that your subjective experience of reality is not a direct copy of the objective world. Your perception is a construction, a hypothesis, a best guess generated by your brain based on sensory data and a lifetime of learned rules. The mindfuck is realizing that the very processes that allow you to see the world so effectively are the same ones that make you susceptible to these deceptions. The system's greatest strengths are also the source of its predictable failures. This understanding fosters a healthy skepticism about the absolute reliability of our senses and opens up a space of wonder at the incredible complexity of the neural machinery that generates our visual world. As you continue your journey towards sleep, allow your mind to gently recall these visual paradoxes. The two lines that are equal but appear different, the identical gray squares that seem to be shades apart, the static image that subtly squirms in the corner of your eye. See these not as errors but as clues, as windows into the secret workings of your own mind. Appreciate your brain as an active interpreter, a tireless artist painting a coherent world for you based on powerful assumptions. Find deep relaxation in letting go of the need for your perception to be a perfect mirror. Instead, rest peacefully within the beautifully constructed, sometimes illusory, and always fascinating reality that your brain creates for you, moment by moment. Auditory illusions. Having explored how our visual system can be deceived, let us now turn our ears to the equally mysterious and fascinating world of auditory illusions. Just as our eyes construct a visual reality, our ears and brain work together to interpret sound waves, and this interpretive process can also be tricked in profound and mind-bending ways. Auditory illusions reveal that what we hear is not a simple recording of sound waves, but a complex construction influenced by context, expectation, and the interaction between our senses. They are powerful demonstrations of how our brain creates a sonic reality, filling in gaps and making best guesses to produce a coherent auditory experience. Tonight, we will explore two classic examples: the endlessly ascending Shepard tone and the sense-blending McGurk effect, each a secret of perception that questions the objective nature of what we hear, inviting deep relaxation through listening to the very process of perception itself. Let's begin with the Shepard tone, named after cognitive scientist Roger Shepard. Listen closely in your mind's ear. Imagine a musical tone that seems to be constantly rising in pitch, like a scale that never ends. It climbs and climbs and climbs, yet it never seems to get any higher. It feels like you are ascending an infinite staircase of sound. This is the Shepard tone illusion. It is created by layering several sine waves, separated by an octave, and playing them in a loop. As the loop progresses, the pitch of each individual wave rises. However, the volume of the higher frequency tones is subtly faded out while the volume of the lower frequency tones is faded in. This clever manipulation of volume and frequency means there is no discernible beginning or end to the scale. Your brain, trying to follow the rising pitch of the most prominent tones, perceives a continuous ascent. But because new, lower tones are always fading in to replace the highest ones that fade out, the overall pitch range never actually changes. The sense of endless ascent is a pure illusion, a phantom melody created by exploiting how our brain tracks pitch changes over time. The shepherd tone is a mind fuck for our auditory system because it violates our fundamental understanding of musical scales. Scales are supposed to have a beginning and an end. They are supposed to go somewhere. The shepherd tone goes nowhere and everywhere at once, creating a sense of perpetual, unresolved motion. It's the auditory equivalent of one of M.C. Escher's impossible staircases. It reveals that our perception of pitch is not just about absolute frequency, but about the relationship between frequencies and how they change over time. By carefully manipulating these relationships, sound engineers and musicians can create a perception of endless motion from a finite, looping set of sounds. It's a beautiful demonstration of how the brain's attempt to find a coherent pattern can be guided into perceiving an impossible one. Now, let us turn to an illusion that reveals the surprising and powerful interaction between our senses, the McGurk effect. This illusion demonstrates that what we hear can be dramatically influenced by what we see. Imagine you are watching a video of a person's face. The audio track is playing the sound ba 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 repeatedly. If you close your eyes and just listen, you will clearly hear ba. Now, imagine you open your eyes and watch the person's lip movements, but the audio track remains exactly the same. However, the person on screen is visibly making the lip movements for the sound ga ga ga. Suddenly, what you consciously perceive yourself hearing changes. Most people will now report hearing the sound da da da. Your brain has taken the auditory information, ba, and the visual information, ga, and because they conflict, it has created a third, entirely new perception, da, as a kind of plausible compromise. If you close your eyes again, the sound immediately reverts to ba. The physical sound wave entering your ear never changed, but your subjective experience of that sound was completely altered by conflicting visual cues. The McGurk effect is a stunning demonstration of multisensory integration. It reveals that our brain does not process sensory inputs in isolated bubbles. Instead, it constantly combines information from different senses to create a single, unified model of reality. In most situations, this is incredibly effective. Seeing someone speak helps us understand them better, especially in noisy environments. Our brain trusts the visual information about lip movements and uses it to clarify ambiguous auditory signals. The McGurk effect is a paradoxical situation where this normally helpful integration process leads to a perceptual error, a veridical hallucination of a sound that isn't objectively there. It shows that vision can, in some cases, literally override what our ears are telling us. This psychology mystery forces us to question the idea of pure listening. It suggests that our auditory experience is never just about sound waves. It's a construction influenced by our other senses, our expectations, and our brain's relentless drive to create a coherent story about the source of the stimuli. That this sound is the brain's best guess, its most plausible solution to the conflicting sensory evidence it is receiving. It is creating a reality that best fits all the available data, even if that reality doesn't match the physical stimulus from any single sense. These auditory illusions, like their optical counterparts, are not mere quirks. They are fundamental clues to the secrets of perception. They show us that our brain is an active inferential engine, not a passive microphone. The shepherd tone reveals how the brain constructs patterns of motion and time based on relational cues. The McGurk effect reveals how the brain constructs unified, multisensory objects by integrating, and sometimes compromising, information across different channels. Both demonstrate that our conscious perceptual experience is a final draft summary, a polished story presented to our awareness after a vast amount of unconscious editing, integration, and interpretation has already taken place. As you continue to relax deeply, listen to the sounds around you, and the sound of this voice. Acknowledge that your experience of these sounds is not a direct transmission, but an intricate construction. Imagine the shepherd tone, an endless upward spiral of sound, a river that flows forever uphill. Imagine hearing b, but seeing j, and perceiving da, a fusion of senses creating a new reality. Let these illusions dissolve any rigid belief in the absolute truth of your senses. Find peace in knowing that your brain is a masterful synthesizer, constantly weaving together different streams of information to create the rich, coherent, and sometimes surprising auditory world you experience. Resting calmly within the symphony of your own perception, aware of the silent, creative work happening beneath the surface of what you hear. The role of expectation in perception. We have seen how ambiguous images and sensory illusions can reveal the constructive nature of perception. Now, let us delve deeper into one of the most powerful forces that shapes this construction: the force of expectation. Your brain is not a passive observer, waiting for sensory information to arrive. It is a proactive, prediction machine, constantly generating hypotheses about the world based on your past experiences, your knowledge, your context, and your current goals. This flow of information from your mind's higher-level knowledge down to influence lower-level sensory processing is known as top-down processing. The profound, often unconscious role that your expectations play in determining what you actually perceive is a deep secret of perception. It's a psychology mystery that reveals how much of what we see, hear, and feel is shaped by what we expect to see, hear, and feel. It fundamentally questions the idea of objective, unbiased perception, suggesting that our reality is profoundly colored by the lens of our own beliefs and history, inviting deep relaxation through acknowledging the predictive power of your own mind. Think of top-down processing as your brain constantly making educated guesses to help interpret the world more efficiently. The sensory information coming from the world, bottom-up data, is often noisy, incomplete, and ambiguous. Instead of trying to build a picture of reality from scratch in every single moment, your brain uses your vast store of knowledge and prior beliefs to create a predictive model of what is likely to be out there. It generates an expectation, and then uses incoming sensory data primarily to confirm or correct that expectation. This is incredibly efficient. It allows us to read messy handwriting, understand speech in a noisy room, and recognize familiar objects from fleeting, partial glimpses. Our brain fills in the gaps based on what it expects. Let's consider some examples. If you see the sequence TC, with the middle letters of the and cat cleverly designed to be the exact same ambiguous shape, you will effortlessly read it as the cat. Your brain uses the context of the words and your knowledge of English to interpret the ambiguous shape as an H in the first word and an A in the second. Your top-down knowledge of language overrides the identical bottom-up sensory data, leading you to perceive two different letters. This happens so automatically, so seamlessly, that we are rarely aware of the powerful interpretive work our brain is doing. Your expectation to see meaningful words shapes what you see. The role of expectation is also powerful in auditory perception. If you are told to listen for a certain word or phrase in a noisy audio recording, you are far more likely to hear it, even if it's very faint or not even there. Your brain, primed by the expectation, will actively search for patterns in the noise that match the target, a phenomenon known as the phonemic restoration effect. This is why we sometimes mishear song lyrics, our brain substituting a plausible phrase for the one that is actually sung. The context provided by the rest of the song, combined with our linguistic expectations, creates the perception. Our emotional state also creates powerful expectations that color our perception. If you are feeling anxious or fearful while walking down a dark street, you are more likely to interpret ambiguous shapes in the shadows as potential threats. A tree branch becomes a menacing figure, the rustle of leaves becomes footsteps. Your emotional state creates a top-down filter of threat, causing you to interpret neutral sensory data in a negative light. Conversely, a state of happiness can lead you to perceive the world and the people in it more positively. Your emotions generate expectations about the world, which then shape your conscious experience of it. This principle is also the foundation of the placebo effect's influence on perception, which we have explored. The expectation of pain relief can genuinely cause a reduction in the perceived intensity of pain. The brain's top-down prediction of less pain actually modulates the processing of incoming pain signals from the body, changing the subjective experience. The belief, the expectation, directly alters the perceptual reality. The mindfuck inherent in top-down processing is the realization of how much of our perceived reality is a projection of our own mind. We feel like we are objectively reading the world, but in reality, we are meeting the world halfway, actively co-creating our experience based on our internal models. This questions the very idea of a purely objective observer. Our past experiences, our cultural learning, our language, our current mood, and our immediate goals are all constantly and unconsciously shaping the reality we perceive in this very moment. This is why two people can witness the exact same event, a political rally, a complex social interaction, and come away with wildly different perceptions of what happened. They brought different top-down frameworks, different expectations, to the same sensory data, resulting in two different constructed realities. This psychology mystery is not about a flaw in our system. It is the system's core operating principle. A brain that relied solely on bottom-up processing would be slow, inefficient, and overwhelmed by data. Top-down processing is what makes our perception so fast, robust, and intelligent, allowing us to make sense of a complex and ambiguous world. The illusions and biases it creates are the price we pay for this efficiency. The secret is acknowledging that our perception is not a direct transcript of reality, but a constantly updated hypothesis, a best guess. Understanding the power of expectation can be incredibly liberating. It can foster humility, encouraging us to question our own perceptions and be more open to the possibility that others might see things differently for valid reasons. It empowers us to become more mindful of our own biases and mental states, recognizing how they might be coloring our experience. By consciously managing our expectations, by being open to surprise, and by actively seeking out information that might challenge our predictive models, we can engage with the world more flexibly and accurately. As you continue your journey towards sleep, become aware of the subtle play of expectation in your own mind. Notice how you anticipate the next sound, the next sensation, the next thought. Acknowledge that your brain is not just receiving the present moment, but actively predicting it, creating it based on the past. Let this understanding bring a sense of profound peace. Your brain is creating your reality not as a deception, but as an act of profound efficiency and intelligence. Find deep relaxation in trusting this process, while also knowing its nature. Letting go of the need for absolute objectivity and resting calmly within the fluid, predictive, and deeply personal world constructed by your own remarkable mind. The brain's filling-in mechanisms. We often trust our vision to provide a seamless, complete picture of the world, a panoramic view without any gaps or holes. Yet, built into the very hardware of your eyes is a significant flaw: the blind spot. In the back of each of your eyes, at the point where the optic nerve connects to the retina, there are no photoreceptor cells, no rods or cones. This creates a small but complete gap in your visual field, an area from which you receive absolutely no visual information. You should, by all rights, perceive two black holes floating in your vision at all times. But you don't. Your experience is one of a continuous, uninterrupted visual world. This is because your brain, in its relentless quest to create a coherent and useful model of reality, actively and unconsciously fills in this missing information. This remarkable act of perceptual fabrication, most clearly demonstrated by the blind spot example, reveals one of the most profound secrets of perception. Your brain is not just an interpreter but a confabulator, a storyteller that invents sensory data to create the illusion of a complete and seamless reality. This psychology mystery questions the very integrity of our visual field and demonstrates that we are always experiencing a world that is, in part, a sophisticated and convincing fiction created by our own minds, inviting deep relaxation through accepting this creative act as you fall asleep. Let's explore this filling-in mechanism more deeply. The process is not a conscious guess. It is an automatic, pre-attentive function of the visual cortex. When faced with the gap in information from the blind spot, the brain doesn't just leave a blank space. Instead, it takes cues from the surrounding visual information and makes an educated, best guess about what should be there, and then it paints that guess into your conscious perception. If your blind spot falls on a uniformly patterned wallpaper, you don't see a hole in the pattern. You see the pattern continue uninterrupted. Your brain seamlessly extends the surrounding texture and color into the void. If it falls on a solid blue wall, you see solid blue. It interpolates from the surrounding data to create a plausible and continuous experience. This is not just ignoring the gap. It is actively creating perceptual content to fill it. You can demonstrate this to yourself with simple exercises. If you close one eye and stare at a fixed point while a small object is moved into your blind spot, the object will literally disappear from your conscious perception. But you won't see a black hole where it was. You will see the background pattern, the wall, the page, as if it were complete. This is a startling, first-hand experience of your brain actively editing your reality, removing an object and replacing it with fabricated background information. The implications of this filling-in mechanism are vast and extend far beyond the anatomical blind spot. It suggests that this process might be a general principle of perception. Our sensory input from the world is always incomplete and noisy. The brain is constantly filling in gaps, not just in the blind spot, but in our peripheral vision, which is much lower resolution, during the brief moments of blindness when our eyes move in rapid saccades, and whenever sensory data is ambiguous or occluded. The smooth, high-resolution, stable visual world we experience is a testament to the brain's incredible ability to construct a coherent whole from fragmented, imperfect data. It is a masterful illusion, a controlled hallucination tethered to sensory input. This psychology mystery forces us to question what it means to see something. Does seeing require a direct, unbroken causal chain from object to photoreceptor to conscious experience? The blind spot shows that this is not the case. We can have a conscious visual experience of something, the filled-in pattern, in a location where there is no corresponding sensory input. This profoundly challenges naive realism, the intuitive belief that we perceive the world directly as it is. It suggests that our perceptual reality is less like a photograph and more like a constantly updated digital painting, where a sophisticated software, our brain, uses clever algorithms to fill in missing pixels based on the surrounding data. This raises further philosophical questions. If the brain is actively fabricating parts of our visual experience to maintain coherence, how can we be sure about the veracity of any part of our perception? While the filling in for the blind spot is based on simple interpolation from adjacent areas, could this mechanism also be influenced by higher-level top-down processing, like our expectations, beliefs, or desires? Could the brain fill in details that align with what we want or expect to see? This possibility blurs the line between perception and imagination, suggesting that the reality we experience is always a blend of sensory fact and cognitive fiction. The enigma of filling in lies in its seamlessness and its subjective reality. We don't feel like our brain is guessing or fabricating. We experience the filled-in portion with the same sense of reality as the parts based on direct sensory input. There is no tag in our consciousness that says, this part is real, this part is a confabulation. The brain presents the entire construction as a unified, veridical whole. This is a mind-fuck of a fundamental nature. The very fabric of our visual awareness contains patches that are woven from pure neural inference, yet we cannot tell the difference. Understanding the brain's filling-in mechanisms doesn't mean we should distrust our senses entirely. This process is highly adaptive and works incredibly well, allowing us to navigate a complex world with remarkable success despite the limitations of our sensory hardware. It allows us to perceive whole objects even when they are partially hidden, and to experience a stable visual world despite the constant jerky movements of our eyes. It is a feature, not just a bug. However, acknowledging this secret of perception should instill a deep sense of intellectual humility. It reveals that our connection to the world is always interpretive, always constructive, always a product of the brain's tireless effort to create a coherent narrative from limited information. As you continue to relax deeply, become aware of the field of perception behind your closed eyes. The darkness is not uniform but a shifting, patterned space. Consider that even this simple experience is a construction of your brain. Now, contemplate the hidden blind spot in your visual field, a void that your brain so skillfully papers over that you never notice its existence. Appreciate the silent, creative work your brain does in every moment, filling in the gaps, smoothing the edges, weaving together a complete and seamless tapestry of reality for you to experience. Find peace in this understanding. Let go of the need for perception to be a perfect mirror of the world. Instead, trust in the remarkable ability of your mind to create a beautiful, functional, and coherent world for you, resting calmly within the wonderfully crafted and partially invented landscape of your own perception as you fall asleep. Color constancy. Let us now explore a subtle yet constantly operating, perceptual miracle that allows us to experience a stable and predictable world. Color constancy. Imagine a red apple. You see it indoors under the warm yellowish glow of an incandescent bulb. You then take it outside into the cool bluish light of an overcast day. You then see it under the direct, bright light of the midday sun. In each of these situations, the actual wavelengths of light reflecting from the apple's surface and entering your eyes are dramatically different. The physical data is constantly changing. Yet, you continue to perceive the apple as being the same consistent shade of red. This remarkable ability of our brain to perceive the color of an object as relatively constant despite significant changes in the illumination conditions is color constancy. It is a profound secret of perception, demonstrating that we do not perceive the raw wavelengths of light reaching our eyes. Instead, our brain creates our reality of color by performing a complex, unconscious calculation to discount the illuminant and infer the object's true underlying surface property. This psychology mystery reveals that color is not a simple property of light, but a sophisticated construction of the mind, designed to provide a stable perception of the world. To grasp the depth of this accomplishment, we must first understand that the color of an object is not something inherent in the object itself. An object's surface has a property called reflectance. its tendency to absorb some wavelengths of light and reflect others. A red apple absorbs most wavelengths but reflects light in the long wavelength, red, part of the spectrum. The light that actually reaches your eye is a combination of the object's reflectance properties and the properties of the light source illuminating it. A white light source contains a full spectrum of wavelengths. A yellowish light source contains more long wavelengths. A bluish light source contains more short wavelengths. Therefore, the physical data, the specific mix of wavelengths, hitting your retina from the apple under a yellow light is objectively different from the data hitting your retina under a blue light. If our perception of color were a simple, direct measurement of the wavelengths entering our eye, the apple would appear to change color dramatically as we moved it from one lighting condition to another. It might look reddish-yellow indoors and purplish-red outdoors. The world would be a chaotic, unstable swirl of shifting colors, making it difficult to identify objects reliably. This is not what we experience. We experience a stable world where objects retain their characteristic colors. This is because your brain performs an incredible, unconscious feat of computational inference. It takes the raw data from the photoreceptor cells in your retina, the cones, which are sensitive to different parts of the spectrum, and using various cues attempts to separate the properties of the light source, the illuminant, from the intrinsic reflectance properties of the object's surface. It essentially tries to answer the question, what is the true underlying color of this surface independent of the light that is currently shining on it? Your conscious experience of color is the answer to this calculation, not the raw data itself. How does the brain achieve this? It uses several cues and assumptions. It looks at the overall color balance of the entire visual scene to estimate the color of the illuminant. If the whole scene has a yellowish cast, the brain assumes the light source is yellow and subtracts that yellowness from its perception of every object in the scene. It looks for the brightest object in the scene and often assumes it is white, using that as a reference point to calibrate its perception of all other colors. It uses memory and prior knowledge. You know that apples are supposed to be red and bananas are supposed to be yellow, and this expectation can influence your perception, helping to stabilize it against changes in lighting. It also uses information from shadows. The light within a shadow is different from the light in a directly illuminated area, and the brain can use this difference to infer properties of the illuminant. The famous internet phenomenon of the dress in 2015 was a powerful real-world demonstration of color constancy mechanisms at work, and how they can differ between individuals. The photograph of the dress was taken under ambiguous lighting conditions. Some people's brains implicitly assumed the dress was in a shadow, so they subtracted the bluish tint of the shadow and perceived the dress as white and gold. Other people's brains assumed the dress was under a bright yellowish artificial light, so they subtracted the yellow and perceived the dress as blue and black, which it objectively was. The same ambiguous sensory data led to two dramatically different, yet stable, perceptual realities, all due to different unconscious assumptions about the lighting. It was a global mind fuck, revealing that even something as seemingly basic as color is a subjective construction. This psychology mystery forces us to question our direct realist intuitions. Color is not out there in the world as we perceive it. It is a product of an interaction between a surface, a light source, and a complex computational process in a brain. It is an invention of the nervous system, a useful way of representing surface reflectance properties that aids in object identification and navigation. The stability of color in our experience is not a passive reflection of a stable world, but an active achievement of our perceptual system, a testament to its power to create a consistent and useful model of reality. Contemplating color constancy can foster a deep sense of wonder at the silent, sophisticated intelligence operating within your own mind. In every moment, your brain is solving complex inverse problems, disentangling light from surface, to present you with a stable, meaningful world of colored objects. It is a constant, effortless act of creation that we take completely for granted. As you continue to relax deeply, become aware of the colors in your memory or imagination. A red apple, a blue sky, green grass. Acknowledge that your experience of these stable colors is a remarkable construction. A secret of perception that allows you to see a consistent world despite the ever-changing light. Appreciate the unconscious calculations your brain performs to discount the illuminant and reveal the true color of things. Find peace in the stability of your perceptual world, while simultaneously recognizing it as a beautiful, intricate creation of your own mind, resting calmly within the vibrant, consistent, and masterfully constructed colorscape of your reality as you fall asleep. Size constancy. Let us now explore another fundamental perceptual miracle, a close cousin to color constancy, that is absolutely essential for our ability to navigate a stable, three-dimensional world. This is the phenomenon of size constancy. Consider a person walking away from you down a long hallway. As they get further away, the actual image they project onto your retina gets progressively smaller and smaller. If you were to hold up your thumb, you could eventually block out their entire image. Yet, you do not perceive the person as physically shrinking into a tiny miniature. Your brain, in its profound wisdom, understands that they are simply moving further away, and you continue to perceive them as being their normal, consistent size. This remarkable ability of our perceptual system to perceive an object as having a constant size, despite dramatic changes in the size of the retinal image it casts due to varying distance, is size constancy. It is a crucial secret of perception, demonstrating how our brain actively creates reality by integrating retinal image size with cues for depth and distance. This psychology mystery reveals that our experience of size is not a direct reading of sensory data, but a sophisticated, unconscious calculation, a best guess about the true, objective size of things in the world. The challenge the brain faces is known as the inverse problem. The two-dimensional image on the retina is inherently ambiguous. A small object nearby and a large object far away can project the exact same sized image onto your eye. How does the brain resolve this ambiguity to determine the object's true size? It does so by becoming a masterful detective, unconsciously using a variety of depth perception cues, which we will explore in more detail later, to estimate the object's distance. These cues include binocular vision, motion parallax, linear perspective, texture gradients, and relative size. Once the brain has an estimate of the object's distance, it performs an unconscious calculation, often referred to as the size-distance scaling mechanism. It essentially takes the size of the retinal image and multiplies it by the perceived distance to arrive at a perception of the object's actual, stable size. So, as a person walks away, their retinal image size decreases, but your brain's estimate of their distance increases, and these two changes cancel each other out, resulting in the perception of a constant size. This process is so automatic and effective that we are rarely aware of the immense computational work involved. It is what allows us to experience a world of stable, reliably sized objects, a world we can confidently navigate. Without size constancy, the world would be a bizarre, warping place where people and objects would seem to shrink and grow wildly as they moved relative to us. Driving a car or even just walking through a room would be incredibly disorienting and dangerous. The power and mechanism of size constancy are most dramatically revealed when it is tricked, leading to powerful optical illusions of size. The Ponzo illusion, which we touched upon earlier, is a classic example. Two identical lines are placed on a drawing of receding railway tracks. The line placed further away, higher up between the narrower part of the tracks, is perceived as much larger. This is because the linear perspective cues scream, distance, to the brain. Your brain applies size-distance scaling. It assumes the further line must be larger to cast the same size retinal image as the nearer line, and thus you perceive it as larger. The illusion is a direct consequence of a normally adaptive size constancy mechanism being misapplied to a 2D image. Similarly, the Ames room is a famous, powerful illusion that manipulates depth cues to distort size perception. It is a specially constructed trapezoidal room that, when viewed from a specific peephole, appears to be a normal rectangular room due to carefully designed perspective tricks. When two people of the same height stand in the two back corners of the room, one appears to be a giant and the other a dwarf. This is because one corner is actually much further away from the viewer than the other. However, because the visual cues make the room appear rectangular, your brain assumes both individuals are at the same distance. Therefore, when faced with two different sized retinal images, it abandons size constancy and concludes that the people themselves must be dramatically different sizes. The illusion pits the assumption of a normal room against the principle of size constancy, and the assumption of the room wins, creating a powerful distortion of perceived size. The moon illusion is another famous example. Why does the moon look so enormous when it is near the horizon, compared to when it is high in the sky, even though its retinal image size is virtually identical in both positions? One leading theory suggests that when the moon is near the horizon, our brains perceive it as being much further away than when it is overhead, due to the presence of terrestrial depth cues like trees, buildings, and atmospheric haze. The brain, applying the size-distance scaling mechanism, concludes that if the moon is that far away yet still casts such a large retinal image, it must be truly gigantic. When the moon is overhead in an empty sky, there are no depth cues, and the brain might perceive it as being closer and therefore smaller. The perceived size of the moon is a construction based on its perceived distance. These illusions and the everyday miracle of size constancy reveal a profound secret of perception. The size of objects in your conscious experience is not a direct report of sensory information. It is a conclusion, a hypothesis, an inference calculated by your brain. It is a part of the stable, user-friendly reality your brain creates to make the world predictable and navigable. This psychology mystery questions the very idea that we see size directly. Instead, we perceive a calculated property that our brain has deemed to be the most likely, true size of an object in the three-dimensional world. As you continue to relax deeply, become aware of the perceived space around you. Imagine the objects in the room, both near and far. Acknowledge the silent, constant calculations your brain is performing to present you with a world of stable, reliably sized objects, regardless of their distance. Appreciate the Ames room, the Ponzo illusion, the moon illusion, not as tricks, but as revelations, as clues to the sophisticated mechanisms of your own mind. Let go of the belief that you see a simple projection of the world. Instead, find peace in the knowledge that you are experiencing a rich, stable, 3D model of reality, masterfully constructed in every moment by the hidden workings of your brain, resting calmly within the wonderfully consistent, yet deeply inferential, world of your own perception. The placebo effect in perception of pain/health. Let us now turn our focus inward to one of the most powerful and enigmatic demonstrations of how the brain creates reality, not just our perception of the external world, but our internal experience of our own bodies. We explore the placebo effect, specifically its profound influence on our perception of pain and health. A placebo, from the Latin I shall please, is an inert substance or sham procedure that has no direct pharmacological effect. Yet, when a person believes it is a genuine treatment, it can produce real, measurable, and sometimes dramatic therapeutic outcomes. A sugar pill can alleviate chronic pain. A saline injection can reduce symptoms of Parkinson's. A sham surgery can be as effective as a real one for certain conditions. This is not simply a matter of imagination or faking it. The placebo effect is a genuine psychobiological phenomenon, a deep psychology mystery that reveals the astonishing power of belief, expectation, and context to directly modulate our most visceral sensations and our sense of well-being. It is a powerful secret of perception that questions the very boundary between mind and body, inviting deep relaxation through contemplating the profound healing potential held within your own mind as you fall asleep. The perception of pain provides the most studied and compelling evidence for the placebo effect. Pain is not a simple, direct signal of tissue damage. It is a complex experience constructed by the brain, influenced by sensory input, but also profoundly shaped by emotional and cognitive factors. The same physical stimulus can be perceived as more or less painful depending on our attention, our emotional state, our past experiences, and crucially, our expectations. This is where the placebo comes in. When a patient is given a placebo and told it is a powerful analgesic, their expectation of pain relief can trigger the brain to activate its own internal pharmacy. Neuroscientific research has shown this process in stunning detail. The belief in impending relief can cause the brain to release endogenous opioids, the body's natural, morphine-like painkillers. These chemicals bind to opioid receptors in the brain and spinal cord, genuinely dampening the transmission of pain signals and reducing the subjective feeling of hurt. Brain imaging studies, fMRI, show that placebo analgesia activates regions of the prefrontal cortex involved in expectation and cognitive control, which in turn modulate activity in brain areas that process the emotional and sensory aspects of pain, like the anterior cingulate cortex and the insula. In essence, your belief in the placebo acts as a top-down signal that tells your brain to turn down the volume of its own pain perception. The relief is real because the brain has changed its own chemistry and processing in response to the belief. This is a clear demonstration of the mind directly regulating the body's most primitive and powerful sensations. The power of the placebo is not limited to just opioids. Expectations of reward and well-being can also trigger the release of dopamine, a neurotransmitter associated with motivation and pleasure. This may play a role in how placebos can alleviate symptoms and conditions like depression or Parkinson's disease, which involve the dopamine system. The context of the treatment powerfully shapes these expectations. A placebo administered by a warm, empathetic, and confident healthcare provider is consistently more effective than one given by a dismissive or uncertain one. The ritual of the therapeutic encounter, the consultation, the white coat, the medical setting, all contribute to a powerful expectation of healing, which the brain then helps to realize. Even the perceived cost of a placebo matters. Studies have shown that a placebo pill described as expensive provides significantly more pain relief than an identical pill described as being on sale. Our brains equate cost with efficacy, and this belief translates into a stronger physiological response. The placebo effect also profoundly influences our perception of overall health and symptoms beyond pain. In clinical trials for antidepressants, a significant portion of the improvement seen in patients is often attributable to the placebo effect. The hope and expectation of getting better, combined with the supportive context of being in a trial, can lead to genuine improvements in mood and outlook. For conditions with a large subjective component like irritable bowel syndrome, chronic fatigue, or anxiety, the placebo response can be particularly robust. The mind's interpretation of bodily signals is key to these conditions, and placebo-induced expectations can directly alter that interpretation, leading to a reduction in perceived symptoms. The mystery deepens when we consider the potential limits and scope of this effect. While placebos are powerful at modulating subjective experiences like pain, nausea, and mood, their ability to affect objective disease pathology is more limited and controversial. A placebo is unlikely to shrink a tumor or kill a virus. However, by reducing stress, alleviating symptoms, and promoting positive neurochemical changes, it's possible that placebos can have indirect positive effects on the immune system and the body's overall ability to heal, though this is a complex area of ongoing research. The mind fuck of the placebo effect is its radical challenge to a simplistic, mechanistic view of the body. It shows that our bodies are not just machines that are fixed by external chemicals. They are dynamic systems deeply intertwined with our mental states. Belief is not an ephemeral thought, it is a potent biological agent. The narrative we tell ourselves about our health and our treatments can become a self-fulfilling prophecy. This questions the very nature of medicine and healing. It suggests that the art of medicine, fostering hope, building trust, managing expectations, is not just a pleasant extra, but a fundamental therapeutic component capable of unlocking the body's own latent healing capacities. Understanding this secret of perception can be incredibly empowering. It doesn't mean we can simply think ourselves well from any ailment. It means recognizing that our mindset, our beliefs, and our engagement with treatment are active participants in our health journey. By cultivating realistic hope, seeking supportive healthcare relationships, and actively engaging in treatments we believe in, we can create the optimal conditions for our mind-body system to function at its best. It encourages us to see our own minds not as passive observers of our health, but as powerful allies in our well-being. As you continue to relax deeply, bring a gentle awareness to the profound connection between your mind and your body. Feel how a calm thought can soothe your physical being. Contemplate the enigma of the placebo effect, the power of pure belief to release real painkillers, to alter mood, to change the very perception of health. Acknowledge this incredible, innate capacity for self-regulation that resides within you. Let go of any rigid separation between the mental and the physical. Find peace in the understanding that your mind is not just a passenger in your body, but an active co-creator of your physical reality, resting calmly, deeply within the quiet, healing potential of your own integrated being. Embodied perception. For centuries, Western philosophy has often treated the mind as a disembodied entity, a rational thinking thing, separate from the messy realities of the physical body. We've spoken of perception as a process of the brain interpreting data from the senses. But what if this picture is incomplete? What if the state of our entire body, its posture, its movements, its physiological state, fundamentally shapes and influences what we perceive? This is the core idea behind the fascinating field of embodied perception or embodied cognition. It proposes that perception is not just something the brain does, but something the whole organism does. Our physical bodies are not passive vehicles for our minds. They are an integral part of our perceptual system, actively influencing how we see, feel, judge, and understand the world. This secret of perception is a profound psychology mystery that questions the mind-body divide, revealing that how your brain creates reality is deeply grounded in the physical realities of your embodiment. Contemplating this deep connection can be a powerful pathway to deep relaxation and a more integrated sense of self as you fall asleep. Let's explore some of the ways our body state affects what we see and feel. Consider something as simple as perceiving distance. Traditional models would suggest this is a purely visual calculation done by the brain. Yet, research in embodied perception has shown that our perception of distance is influenced by our physical state and potential for action. For example, studies have found that people wearing a heavy backpack perceive a hill as steeper and a distance as longer than those without a backpack. The increased physical effort required to traverse the distance is unconsciously factored into the perceptual experience itself. The world literally looks different when you are tired or burdened. Similarly, people who are less physically fit tend to perceive distances as greater than those who are more fit. Our perception of space is not neutral and objective. It is scaled to our body's current abilities and energy levels. This extends to our social perceptions as well. The simple act of holding a warm cup of coffee versus a cold one has been shown to influence how we judge other people. Participants holding a warm cup are more likely to perceive a stranger as having a warm personality, generous, caring, while those holding a cold cup are more likely to perceive them as having a cold personality. This demonstrates a deep, unconscious metaphoric link between physical temperature and social warmth, where a bodily sensation directly influences a complex social judgment. Our language is full of these metaphors: a heavy topic, a close friend, a rough day, and embodied cognition suggests these are not just figures of speech, but reflections of a deep integration of physical and abstract concepts in our minds. Our posture also shapes our thoughts and feelings. Studies on power posing suggest that adopting expansive, open postures can not only make us feel more confident and powerful but can even lead to measurable changes in hormone levels associated with confidence and stress. Conversely, slumping or adopting a constricted posture can influence mood and self-perception negatively. The state of your body sends constant feedback to your brain, shaping your emotional and cognitive landscape. This is why practices like yoga or Tai Chi, which focus on mindful posture and movement, can have such profound effects on mental well-being. They work by changing the body to change the mind. Even the simple act of facial expression, according to the facial feedback hypothesis, can influence our emotional state. Forcing a smile, even a fake one, can sometimes genuinely improve your mood, while furrowing your brow can make you feel more critical or annoyed. The physical action of the facial muscles sends feedback to the brain that helps to shape the emotional experience. We don't just smile because we are happy. We can sometimes feel happier because we are smiling. The body's expression is not just an output of emotion, it's also an input. The mindfuck of embodied perception is its complete reversal of our traditional, mind-centric view of existence. We tend to think, my mind perceives the world and then tells my body how to act. Embodied cognition suggests the arrow also flows powerfully in the opposite direction. My body's state and potential for action in the world directly shape how my mind perceives it. The brain and body are not a master and a servant. They are in a constant, dynamic, reciprocal loop. Your consciousness is not a disembodied pilot flying a biological machine. It is an emergent property of the entire, integrated mind-body environment system. Your perception is not just of the world, it is shaped for acting within the world with the specific body you have. This psychology mystery challenges us to understand the precise mechanisms of this feedback loop. How exactly does the physiological state of fatigue or the weight of a backpack get translated into the visual system's calculation of distance and slope? How does the physical sensation of warmth activate conceptual networks related to social trust? These questions are at the forefront of modern cognitive science, requiring an integrated understanding of neuroscience, psychology, and even robotics, where building embodied robots has revealed how crucial a body is for developing intelligent, adaptive behavior. Understanding embodied perception can have a profound impact on our well-being and how we navigate our lives. It validates the wisdom of practices that focus on the body as a path to mental and emotional health. It suggests that if we want to change our perspective, sometimes the most effective way is to change our physical state, to stand up straighter, to go for a walk, to breathe more deeply, to simply hold a warm drink. It reminds us that our perception of the world is not a fixed, objective truth, but a fluid, subjective experience, intimately tied to the shifting state of our physical selves. It grounds our entire mental life, our thoughts, our feelings, our perceptions of reality, in the tangible experience of our bodies. As you continue to relax deeply, bring your awareness to the physical sensations of your own body right now. The feeling of weight, of contact with the surface beneath you, the rhythm of your breath, the temperature of the air. Contemplate the idea that these physical states are not just the background to your perception, but are actively shaping it. They are influencing how you feel, how you think, how you would perceive the space around you. Let go of the idea of your mind as something separate from your body. Instead, feel them as a unified, integrated whole, a single system of embodied awareness. Find peace in this profound connection, this grounding of your consciousness in the physical reality of your being, resting calmly, deeply, within the quiet wisdom of your embodied self. Cross-modal perception. Let us now delve into one of the most fundamental and elegant secrets of perception, the constant, seamless dialogue between our senses. We learn as children to name 5 distinct senses: sight, hearing, touch, taste, and smell, and often think of them as separate, independent channels providing discrete information about the world. But this modular view is a profound simplification. The reality your brain creates is not a collage of separate sensory reports, but a unified, integrated, multisensory tapestry. This intricate weaving together of information from different sensory modalities is known as cross-modal perception. It is the reason the crunch of a potato chip enhances its taste, why a ventriloquist's trick works, and why seeing a ball bounce and hearing a thump at the same time feels like a single, unified event. The mystery of cross-modal perception lies in understanding the complex neural mechanisms that bind these disparate streams of information into one coherent whole, questioning the very idea of a purely visual or auditory experience and revealing that our perception is, at its core, a multisensory symphony. Let the boundaries between your senses soften and blur as you fall asleep. The brain's primary objective in perception is not to simply record sensory data, but to create a stable and useful model of the external world and the objects within it. Objects in the world are not just visual or just auditory, they are multisensory. A barking dog is a visual shape, an auditory event, and potentially a tactile and olfactory one as well. To form a coherent concept of the dog, the brain must solve the crucial binding problem on a multisensory level. It must figure out which sights, sounds, and smells belong to the same source and bind them together into a single unified object. This integration process is not a final step, but a constant, dynamic negotiation between the senses, where one sense can profoundly influence, alter, and even override another. We have already touched upon the most famous demonstration of this, the McGurk effect. Hearing the syllable b while seeing the lip movements for results in the perception of da. This is not a compromise our conscious mind makes. It is a pre-attentive fusion that happens deep within the brain's perceptual machinery. It reveals a clear hierarchy. When it comes to speech perception, your brain trusts vision more than hearing, and it will construct a new auditory reality to resolve the conflict. This is a powerful example of vision influencing hearing. This directional influence is common. The ventriloquism effect is another case of visual dominance. Our brain's assumption that sounds should come from their apparent visual source is so strong that it moves the perceived location of the ventriloquist's voice to the puppet's moving mouth. This cross-modal binding of location is essential for our ability to navigate the world, allowing us to immediately locate the source of a sound by looking towards it. When you hear a car horn and turn to see the car, your brain is binding auditory and visual data into a single car event. But the influence flows in many directions. Hearing can also influence vision. In a phenomenon known as the double flash illusion, if a single flash of light is presented on a screen accompanied by 2 brief auditory beeps, many people will report seeing 2 flashes of light. The auditory information, 2 events, overrides the visual information, 1 event, causing the brain to generate a phantom visual percept to create a more coherent multisensory story. The brain decides it is more likely that one of the flashes was missed by the eyes than that one of the beeps was a hallucination, so it creates the missing flash in our conscious perception. The interplay between taste, smell, and even sight is fundamental to our experience of food. As we've explored, what we call flavor is a complex cross-modal construction, primarily arising from the combination of basic taste from the tongue and the rich aromatic information from retronasal olfaction, smell via the back of the throat. But vision also plays a key role. The color of a food or drink creates powerful expectations that can alter its perceived taste. In experiments, people given cherry-flavored soft drinks that are colored orange will often report tasting orange. The visual cue suggestion is so powerful it overrides the actual taste and smell information. Even the shape of a glass can influence the perceived taste of a beverage, and the color of a plate can affect the perceived sweetness or saltiness of the food on it. Our brain uses every available sensory cue to construct the final unified experience of flavor. Touch and hearing are also deeply connected. The sound something makes when we interact with it profoundly influences our perception of its texture and quality. The satisfying click of a well-made mechanical switch, the solid thunk of a car door closing, or the crisp snap of fresh lettuce all contribute to our tactile and qualitative judgment of the object. When the sound is altered or removed, our perception of the object's physical properties can change dramatically. This is why sound design is so critical in product engineering and digital interfaces. The auditory feedback shapes our entire experience of the object. The psychology mystery at the heart of cross-modal perception is how the brain achieves this seamless integration. Neuroscientists are discovering multisensory neurons throughout the brain, cells that respond to stimuli from more than one sense. Brain regions previously thought to be unisensory, like the primary visual or auditory cortex, are now known to receive inputs from other senses, suggesting that integration begins very early in the processing stream. The brain appears to operate on Bayesian principles, constantly weighing the reliability of different sensory inputs and combining them in a statistically optimal way to form its best guess about the state of the world. When one sense is noisy or ambiguous, the brain gives more weight to information from a more reliable sense. The reality your brain creates is a continuously updated, probabilistically weighted fusion of all available sensory data. Contemplating cross-modal perception fundamentally questions the idea of living in 5 separate sensory worlds. It reveals that our subjective experience is a holistic, unified Gestalt, a symphony where the different sensory sections are always playing in concert, influencing and enriching one another. The world you perceive is not a collection of independent inputs, but a single, coherent, multisensory story. This understanding can enhance our appreciation for everyday experiences. The pleasure of a good meal is not just taste, but also the aroma, the visual presentation, the texture, and the sound it makes. The experience of being in a forest is a fusion of the sight of green leaves, the sound of birdsong, the smell of damp earth, and the feeling of the breeze. As you continue to relax deeply, become aware of the symphony of your own senses. Notice how the feeling of the air on your skin might subtly influence your mood, how a distant sound might evoke a visual memory. Acknowledge that the boundaries between your senses are not as solid as you might think. They are constantly conversing, collaborating, weaving together the fabric of your conscious moment. Let go of the idea of a fragmented sensory world. Find peace in the hidden unity of your perception. Appreciate the profound, silent intelligence of your brain as it masterfully conducts this multisensory orchestra, resting calmly within the rich, integrated, and beautifully coherent reality it creates for you as you fall asleep. Subliminal perception. Let us now explore a concept that resides on the shadowy border of consciousness, a topic steeped in controversy, myth, and genuine psychological inquiry: subliminal perception. The word subliminal means below the threshold, and it refers to the idea that stimuli presented too quickly, too faintly, or too obscured to be consciously perceived can still enter our minds and influence our subsequent thoughts, feelings, and perhaps even our actions. This idea exploded into the public consciousness with tales of hidden messages in advertisements and movies, sparking fears of widespread mind control and manipulation. But what is the reality behind the myth? Does subliminal perception truly work in the powerful way popular culture imagines? The answer is a nuanced and complex one, revealing a deep psychology mystery about the division between conscious and unconscious processing. The investigation into what the mind can perceive without awareness questions our very sense of conscious control and agency, demonstrating how the brain creates reality not just from what we see, but also from what we don't know we see. Let this exploration of the mind's hidden depths guide you into a state of deep relaxation as you fall asleep. First, it is essential to dismantle the sensationalized myth. The infamous claims from the 1950s that subliminal messages like "drink Coca-Cola" and "eat popcorn" flashed in movie theaters led to a dramatic increase in sales were a complete fabrication, a marketing hoax later admitted by its creator, James Vickery. Decades of subsequent research have consistently shown that subliminal perception does not work as a tool for powerful, direct behavioral coercion. There is no evidence that a hidden message can compel you to perform a complex action that goes against your existing beliefs, desires, or intentions. The fear of being turned into a consumer puppet by flashing words is unfounded. Our conscious mind, with its goals and values, is a far more robust gatekeeper than these early fears suggested. However, dismissing the concept entirely would also be a mistake. The truth, as revealed by careful laboratory research, is more subtle and in some ways even more fascinating. While subliminal messages cannot force complex behaviors, they can have small, fleeting, and measurable effects on our cognitive and emotional states through a process known as priming. Subliminal priming involves exposing a person to a stimulus outside their conscious awareness, for example, by flashing a word for just a few milliseconds and then immediately masking it, and then observing its effect on a subsequent task. Consider semantic priming. If the word bread is flashed subliminally, participants are often slightly faster to recognize a related word like butter than an unrelated word like chair. They have no conscious memory of seeing bread, yet its presentation has activated a whole network of associated concepts in their brain, warming up the pathway for butter and making it easier to process. This demonstrates that the brain is extracting meaning from stimuli without the involvement of conscious awareness. This unconscious processing is incredibly efficient, constantly categorizing and making connections below the surface. The effects can also be affective or emotional. Subliminally priming participants with positive images, like a smiling face or a kitten, can lead them to rate subsequent neutral stimuli, like an abstract symbol or a person with a neutral expression, more positively. Conversely, negative primes, like a frowning face or a spider, can lead to more negative ratings. This suggests that the brain can process the emotional valence of a stimulus unconsciously, and this faint emotional coloring can then bleed over into our subsequent conscious judgments. The effect is typically very small, a slight nudge in preference, not a dramatic change of heart, but it demonstrates that our feelings and attitudes can be subtly influenced by things we don't even know we've perceived. So, where does the psychology mystery lie? It lies in understanding the capabilities and limits of this vast ocean of non-conscious processing. What kind of information can be processed subliminally, and what requires the spotlight of conscious attention? The evidence suggests that the unconscious mind is very good at processing simple, familiar stimuli, basic shapes, single words, emotional valence, and learned associations. It can handle concrete nouns better than abstract ones. However, it seems to struggle with or be incapable of processing more complex information involving syntax, logic, negation, or novel combinations. The unconscious might register salt, but it likely cannot process the subliminal command, do not buy salt. This complexity barrier is a crucial safeguard, suggesting that conscious, deliberate thought is necessary for higher-order reasoning and goal-directed action. The mindfuck of subliminal perception, therefore, is not about external control but about internal architecture. It reveals that the you that you experience, your conscious stream of thoughts and decisions, is only a small fraction of the total information processing occurring in your brain at any given moment. Your consciousness is like the CEO of a vast corporation, seeing only the executive summaries and making the final decisions, while remaining blissfully unaware of the countless memos, emails, and departmental conversations happening at lower levels. The results of subliminal priming are like faint echoes from those lower levels, subtly influencing the CEO's mood or making certain reports easier to read. It questions the illusion that our conscious mind is in complete command and fully aware of all the information it's working with. It suggests our sense of rational agency might be built upon a foundation of unseen, unconscious influences and associations. This understanding of subliminal perception connects to many other secrets of perception. It reinforces the idea of the brain as a predictive, top-down machine, where unconscious priming can influence the expectations that shape our conscious experience. It relates to the nature of intuition, where a gut feeling might be the conscious manifestation of complex information processed subliminally. It also forces us to consider the ethical implications of modern media, where we are constantly bombarded with rapid-fire images and sounds. While not acting as coercive subliminal commands, this constant stream of information undoubtedly primes our unconscious associations and shapes our feelings and preferences in subtle ways over time. As you continue to relax deeply, let your awareness of the world gently soften. Acknowledge that beneath the threshold of your conscious perception, your brain is silently and ceaselessly processing a vast amount of information, sorting, categorizing, making connections. Let go of the need to be aware of and in control of everything. Find peace in trusting this powerful, efficient, unconscious machinery. Appreciate the mystery of this hidden mental life, not as a source of fear, but as a testament to the incredible depth and capacity of your own mind. The reality your brain creates is shaped by both the light of conscious attention and the subtle shadows of what lies just below. Resting calmly, knowing that you are more than just your conscious thoughts, but a whole integrated being of seen and unseen processes. Pareidolia. Let us now turn our attention to one of the most whimsical, creative, and revealing tendencies of the human mind, the phenomenon of pareidolia. This is the universal human experience of perceiving meaningful patterns, most commonly faces, in otherwise random or ambiguous visual and auditory stimuli. It is the reason we see a man in the moon, animals in the clouds, faces in the patterns of wood grain, or hear hidden messages in the static between radio stations. Far from being a sign of a disordered mind or an overactive imagination, pareidolia is a profound secret of perception, a powerful demonstration of the brain's hyperactive pattern recognition system. It showcases the immense power of top-down processing, where our internal expectations and evolutionary templates are so strong that they actively project meaning and structure onto pure randomness. This psychology mystery fundamentally questions the objectivity of what we see, revealing how eagerly our brain creates reality, sometimes constructing it from the slightest of suggestions. Let the contemplation of these phantom faces and hidden patterns guide you into a state of deep relaxation and wonder as you fall asleep. The origins of pareidolia are believed to be deeply rooted in our evolutionary history. For our ancestors navigating a complex and often dangerous world, the ability to rapidly detect meaningful patterns was a critical survival skill. The most important pattern to detect, without question, was another face. A face could signify a caregiver, a potential mate, a rival, or a predator lurking in the shadows. The evolutionary cost of a false negative, failing to detect a real predator's face camouflaged in the foliage, was catastrophic. In contrast, the cost of a false positive, momentarily thinking a rock formation or a pattern of leaves looks like a face, was negligible, amounting to little more than a fleeting moment of misplaced attention. Consequently, natural selection likely favored brains with a highly sensitive, even overly sensitive facial detection system. We evolved to be pattern seekers on a hair trigger, biased towards assuming the presence of agency and intention in the world around us. Pareidolia is the natural and expected byproduct of this highly adaptive, but error-prone cognitive strategy. This is why faces are the most common subject of pareidolic experiences. Our brains possess specialized neural circuitry, such as the fusiform face area, which is dedicated to processing and recognizing faces with incredible speed and efficiency. This system is so attuned to the general configuration of a face, typically two eyes above a nose and mouth, that even minimal abstract patterns can trigger it. Two dots and a curved line on an electrical outlet, the arrangement of headlights and a grille on a car, the craters on the moon, these simple configurations are close enough to the brain's internal facial template to cause the system to fire, generating the conscious perception of a face. The experience is often not one of imagining a face. For a moment we genuinely see it, complete with a perceived expression: happy, sad, menacing, or surprised. The brain doesn't just find a pattern, it imbues it with emotional and intentional significance. The phenomenon extends beyond vision into the auditory realm. Auditory pareidolia occurs when our brain interprets random noise as meaningful sounds, most often human speech or music. This is the basis for hearing hidden messages in reversed audio tracks or perceiving whispers in the hum of a machine or the rush of the wind. Our brains are so primed to detect the cadence and structure of language that they will impose that pattern onto ambiguous auditory static. The brain is trying to find a signal in the noise, and the most important signal it knows is the human voice. This demonstrates that the same top-down, pattern-projecting mechanism is at work across different sensory modalities. The psychology mystery of pareidolia deepens when we consider its connection to our internal psychological states. Research has suggested that our emotional and motivational states can influence our propensity to experience pareidolia. For instance, individuals who are feeling lonely, anxious, or have a heightened need for social connection may be more likely to perceive faces in random patterns. This suggests that when we crave agency or companionship, our brains may lower the threshold for detecting it, becoming more likely to project human-like features onto the inanimate world. Similarly, in a state of fear or heightened alert, we might be more prone to perceiving threatening figures or faces in ambiguous shadows, as our brain's threat detection system becomes more sensitive. Our inner world of feelings and needs directly shapes the way we structure and interpret the external world of random stimuli. Pareidolia is a quintessential example of top-down processing dominating bottom-up sensory data. The random visual or auditory information is the raw bottom-up input. But this input is ambiguous and lacks inherent meaning. It is the top-down influence, our brain's stored templates for faces and other meaningful patterns, driven by evolutionary programming and current psychological states, that actively organizes this randomness into a coherent, meaningful percept. The reality your brain creates is one where agency and pattern are the default assumption, not just a conclusion drawn from clear evidence. This has profound philosophical implications. It powerfully questions the idea that we are objective observers of the world. It suggests that our perception is inherently projective. We don't just see what is there, we see what our brains are prepared and motivated to see. The line between perception and imagination becomes incredibly thin. This realization can help explain the psychological origins of many beliefs in supernatural or paranormal phenomena, where ambiguous events, a strange shadow, a creak in the night, a random pattern of light in a photograph, are interpreted as evidence of intentional unseen agents like ghosts, spirits, or deities. Pareidolia provides a naturalistic explanation for why humans are so prone to seeing intention and agency in the world, even where there is none. At the same time, this very process is fundamental to human creativity and art. An artist looking at a block of marble might see the figure waiting within it, projecting a form onto the raw material. A poet might find profound meaning and connection in the random arrangement of stars. A musician might hear a melody in the rhythm of the rain. The ability to see one thing as another, to find order in chaos, to project meaningful patterns, is the very engine of metaphor, symbolism, and artistic creation. Pareidolia is not just a cognitive quirk. It is the raw, untutored expression of the same creative, meaning-making impulse that drives human culture. As you continue to relax deeply, allow your mind's eye to soften its focus. Imagine gazing at the gentle, shifting forms of clouds or the subtle, random patterns in the darkness behind your eyelids. Do not consciously search for images, but simply remain open and notice if your mind spontaneously offers them up: a face, an animal, a fleeting landscape. Acknowledge this creative process with a sense of gentle wonder. Recognize it not as a flaw or a trick, but as a profound secret of perception, a glimpse into your brain's ancient, powerful, and ceaseless drive to find meaning and connection in the world. Find peace in knowing that your mind is not a passive mirror but an active artist, constantly painting your experienced reality with the colors of expectation and the shapes of familiarity. Resting calmly, watching the beautiful, phantom patterns emerge and dissolve in the quiet gallery of your own mind as you fall asleep. The impact of culture on perception. We often operate under the deeply ingrained assumption that our basic sensory perception of the world is a universal human constant, a biological given shared by everyone with healthy eyes and ears. We believe that the sky is objectively blue, that a line has a definite length, that the world, out there, presents itself to all of us in the same way. However, a wealth of fascinating research from the fields of anthropology, psychology, and linguistics reveals a more complex and unsettling truth. The culture in which we are raised can profoundly influence, filter, and even fundamentally alter what we perceive. This is the impact of culture on perception. The very language we speak, the physical environment we inhabit, and the social values we internalize can shape everything from our perception of color to our susceptibility to optical illusions. This psychology mystery challenges the notion of a single, objective human experience, suggesting instead a beautiful and complex tapestry of diverse perceptual worlds. It questions the very foundation of what it means to see the world, revealing that how your brain creates reality is a process deeply intertwined with the cultural software running on its biological hardware, inviting deep relaxation through contemplating the vast diversity of human experience as you fall asleep. Let's begin with the captivating case of color perception. The visible light spectrum is a physical continuum of wavelengths, with no sharp boundaries. Yet, most of us perceive it as being divided into distinct categories: red, orange, yellow, green, blue, indigo, violet. We tend to assume these categories are natural and universal. However, the study of different languages reveals that this is not the case. The concept of linguistic relativity, often associated with the Sapir-Whorf hypothesis, suggests that the structure of a language influences its speaker's perception and cognition. When it comes to color terms, different languages carve up the continuous color spectrum in different ways. Some languages, for example, have historically used a single term to cover shades that English speakers would definitively call blue or green. For speakers of such a language, the distinction is less salient. Conversely, some languages make distinctions that are absent in English. Russian, for instance, has two distinct, basic color terms for what English speakers just call blue. Голубой for light blue and синий for dark blue. They are not considered shades of the same color, but as different colors much like red and pink are in English. Fascinatingly, research has shown that this linguistic difference has a perceptual consequence. Russian speakers are measurably faster at distinguishing between two shades of blue if they fall across the голубой/синий boundary than if they fall within the same category. Their language has trained their brain to make this specific distinction more quickly and efficiently. The words we possess literally shape the speed and salience of our perception. The Himba people of Namibia provide another powerful example. Their language has a rich vocabulary for different shades of green, but groups many colors we would call blue or green under a single term. Experiments have shown that they can effortlessly distinguish between shades of green that look identical to a Western observer, yet they struggle to quickly spot a blue square among green ones, a task that is trivially easy for an English speaker. This is not because their eyes are different, but because their cultural and linguistic environment has tuned their perceptual system to prioritize different distinctions in the color spectrum. The reality of color is not a simple reflection of wavelengths. It is a collaborative construction between the eye, the brain, and the cultural linguistic framework one inherits. The impact of culture extends beyond color to our perception of space and our susceptibility to optical illusions. Consider the Muller-Lyer illusion, where a line with outward-pointing fins appears longer than an identical line with inward-pointing arrows. The carpentered world hypothesis, as we've explored, suggests this illusion is stronger for people raised in industrialized societies filled with rectangular buildings, rooms, and furniture. This environment trains the brain to automatically interpret certain 2D line junctions as 3D perspective cues. To test this, researchers Joseph Henrich and his colleagues conducted studies with people from various small-scale societies, including hunter-gatherers living in natural environments with very few straight lines or right angles. The results were clear. Individuals from these non-carpentered worlds were significantly less fooled by the illusion. Their perceptual systems had not been trained by their environment to make the same automatic 3D inferences from those specific 2D cues. This is a powerful demonstration that even a seemingly basic perceptual judgment, like the length of a line, is not a universal constant but is shaped by the visual statistics of the world we grow up in. Cultural differences in attentional style also profoundly affect perception. Psychologists like Richard Nisbet have documented a general tendency for individuals from Western individualistic cultures to engage in analytic perception, focusing on central objects and their attributes, decontextualizing them from their background. In contrast, individuals from East Asian collectivistic cultures tend to engage in holistic perception, paying more attention to the context, the background, and the relationships between objects. In a change blindness task, for example, American participants might be quicker to notice changes in a central object, while Japanese participants might be quicker to notice changes in the background context. This difference in what is considered perceptually salient is not a conscious choice. It is a deeply ingrained cognitive style fostered by different social structures, philosophical traditions, and even parenting practices. The mind-fuck of these cross-cultural findings is its radical challenge to our perceptual solipsism, the naive assumption that everyone else sees the world exactly as we do. It suggests that the obvious and self-evident nature of our own perceptions is, in fact, a culturally specific construction. The reality your brain creates is not just a personal one but a cultural one. The very software your brain uses to interpret sensory data is written in the language of your culture. This psychology mystery lies in understanding the deep plasticity of the human brain. How does culture get under the skin to shape these fundamental perceptual processes? It likely involves a combination of linguistic framing, attentional training, environmental statistics, and the internalization of cultural values, all of which sculpt neural pathways over the course of development. Our brains are not fixed hardware, they are dynamic systems that are constantly being tuned by their environment, and culture is the most significant part of that environment. Understanding the impact of culture on perception is a powerful exercise in empathy and intellectual humility. It allows us to approach cross-cultural interactions with a deeper appreciation for the potential differences in worldview, reminding us that disagreements may sometimes stem not just from different beliefs, but from different ways of fundamentally perceiving the world. As you continue to relax deeply, let the familiar contours of your own perceptual world soften. Imagine for a moment seeing through the eyes of someone from a different culture, a world where colors are divided differently, where illusions lose their power, where the background is as alive as the foreground. Acknowledge that your experience of reality is one beautiful version among many, a masterpiece painted with the unique palette of your language and culture. Find peace in this diversity. Let go of the need for a single universal perception, and instead, appreciate the profound secret that humanity perceives not one world, but a rich spectrum of worlds, all generated by the remarkable interplay of our shared biology and our diverse cultural lives. Resting calmly, a citizen of your own perceptual reality, yet open to the profound mystery of others. The nature of subjective experience. Voiceover, very calm, slow, measured, deeply resonant, almost hypnotic. We now arrive at the very heart of the mystery of perception, the inner sanctum of consciousness itself. We explore the profound enigma known as qualia. The word refers to the introspectively accessible, private, qualitative character of our experiences. It is the what it is likeness of a sensation. Qualia are the raw feelings themselves. The redness of red, the specific pang of a particular sadness, the taste of a strawberry, the warmth of the sun on your skin, the sound of a cello. While we can objectively describe the physical world, the wavelength of light, the chemical composition of a strawberry, the frequency of a sound wave, these descriptions seem to leave something crucial out: the subjective experience itself. The question of what qualia are, how they relate to the physical brain, and why they exist at all, is arguably the deepest secret of perception and is synonymous with the hard problem of consciousness. It is a profound psychology mystery that questions the very ability of objective science to ever fully account for the richness of our inner world. Contemplating the ineffable nature of your own qualia is a direct path to acknowledging the deepest mystery of your existence, inviting deep relaxation through the quiet appreciation of your own inner life as you fall asleep. Let's try to grasp the elusive nature of qualia. Imagine trying to describe the color red to a person who has been blind from birth. You could provide them with all the physical information, the specific wavelengths of light, the way red light stimulates the cone cells in the retina, the neural pathways it activates in the brain. You could give them a complete, exhaustive scientific account of the physics and neurobiology of seeing red. But would they, after learning all of this, know what it is like to see red? Intuitively, we feel the answer is a resounding no. That subjective, qualitative feeling of redness is a quali, the singular of qualia, and it seems impossible to convey through purely objective third-person descriptions. It is private, intrinsic, and seemingly irreducible. This is the essence of the famous Mary's Room thought experiment by philosopher Frank Jackson. If a brilliant neuroscientist, Mary, has learned every physical fact about color vision but has lived her entire life in a black and white room, does she learn something new when she sees the color red for the first time? If she does, it suggests that the subjective experience, the qualia of redness, is a form of knowledge beyond the purely physical facts. The mystery of qualia fundamentally questions the philosophical position of physicalism or materialism, which holds that everything in the universe, including the mind, is ultimately physical. If qualia are real, subjective properties of experience, how can they be accounted for in a purely physical world? How can the objective, quantitative properties of neurons firing, their firing rate, their chemical interactions, their location, give rise to the subjective, qualitative properties of experience? This is the explanatory gap. There seems to be nothing in our understanding of physics or neuroscience that would predict that certain brain states should feel like anything at all, let alone have the specific qualitative character they do. Philosophers have proposed various stances on this deep problem. Eliminative materialists like Daniel Dennett take a radical approach, arguing that qualia, as we typically conceive of them as private, intrinsic, ineffable properties, are actually an illusion, a relic of a pre-scientific folk psychology. They argue that our belief in qualia is a conceptual confusion. While we certainly have discriminatory states in our brain that allow us to react differently to red and green light, the idea that there is an extra, mysterious redness property attached to this state is a mistake. A complete neuroscientific account, they would argue, will eventually explain away the illusion of qualia entirely. For the eliminativist, the only mystery is why we are so prone to this powerful illusion of inner qualitative states. Another physicalist approach, representationalism, suggests that the qualitative character of an experience is identical to the representational content of that experience. The redness of seeing a red apple is not a property of your mind, but rather your mind's representation of the objective property of the apple's surface, its reflectance. Our experience is transparent. As we explored earlier, we look through the mental state to the properties of the object it represents. This attempts to naturalize qualia by locating them in the relationship between the brain and the external world, though it still struggles to explain why representing a certain surface property should feel like anything at all from the inside. Dualists, on the other hand, take the existence of qualia at face value and conclude that they must be non-physical properties. Property dualism, a common modern view, suggests that while the brain is a single physical substance, it has two fundamentally different kinds of properties: physical properties like mass and charge, and mental properties, qualia. In this view, consciousness is a non-physical property that emerges from or is produced by the brain, but it is not reducible to the brain's physical properties. This respects our powerful intuition about the reality of subjective experience but leaves us with the profound mystery of how a physical brain can produce non-physical properties and how those properties can, in turn, affect the physical brain, the problem of mental causation. The enigma of qualia also leads to other mind-bending thought experiments. The inverted spectrum argument asks you to imagine a person who, from birth, experiences colors in a way that is systematically inverted compared to everyone else. When they see a red apple, they have the subjective experience that you have when you see a green apple. However, since they grew up in the same linguistic community, they learn to call that experience red. Their behavior would be indistinguishable from anyone else's. They would stop at red lights, correctly identify red objects, and use the word red consistently. But their inner, subjective experience, their qualia, would be completely different. The problem is there would be no way to ever know. This highlights the profound privacy and incommunicability of qualia, and further questions the link between physical brain states and specific subjective feelings. Ultimately, the nature of subjective experience may be the hardest problem of all because our entire world, all our knowledge, all our science, is built upon it. Qualia are the very data of consciousness. They are not something we observe. They are the very medium of observation itself. To study them scientifically is like trying to see your own eyes without a mirror. You are using the very thing you are trying to observe. As you continue to relax deeply, turn your awareness inward to the simple, direct qualities of this present moment. The feeling of coolness or warmth in the air, the low hum of the ambient sound, the faint pressure of contact. These are qualia. They are the raw data of your existence. Contemplate the profound mystery that these simple feelings represent, a private, inner world of experience arising from the silent, electrochemical activity of your brain. Let go of the need to explain them, to reduce them, to solve them. Instead, simply be with your subjective experience. Appreciate its richness, its immediacy, its ineffable nature. Find peace not in understanding what qualia are, but in simply acknowledging the undeniable reality of your own, resting calmly within the deep, silent, and beautifully mysterious theater of your own mind as you fall asleep. Hallucinations and perception distortion. We have explored the many subtle ways our brain's normal functioning constructs our reality, through illusions, biases, and cultural lenses. Now, let us venture to the edge of typical perception, to explore what happens when this constructive process goes awry, leading to hallucinations and perception distortion. A hallucination is the experience of a seemingly real perception of an object or event when no corresponding external stimulus exists. It is seeing, hearing, feeling, smelling, or tasting something that isn't out there. Perception distortion, on the other hand, involves misinterpreting the qualities of a real stimulus, seeing objects as warped, hearing sounds as distorted, or experiencing a profoundly altered sense of time or self. These phenomena are not just symptoms of severe mental illness. They can occur under various conditions such as sensory deprivation, extreme stress, fever, psychoactive substance use, or during the liminal states between sleep and wakefulness, hypnagogic and hypnopompic hallucinations. Exploring these dramatic deviations from consensus reality provides a powerful, if sometimes unsettling, window into the creative and generative power of the brain. They are a profound psychology mystery that powerfully demonstrates that the reality your brain creates is just one possible version among many, and that the machinery of perception can, under certain conditions, operate entirely on its own, independent of the external world. The most fundamental secret of perception revealed by hallucinations is that the brain possesses the complete capacity to generate a full-blown, convincing perceptual experience entirely from internal sources. When you dream at night, you are essentially having a prolonged, immersive, multisensory hallucination. The dream world feels real while you are in it, yet it is generated without any corresponding sensory input. Hallucinations in a waking state are like a dream breaking through into reality. This tells us that the neural machinery for seeing a tree can be activated either by bottom-up signals from the eyes looking at a real tree, or by top-down signals originating from within the brain itself. The conscious experience of seeing a tree might feel identical in both cases. This profoundly questions the authority of our senses. If the brain can create a perception that is indistinguishable from one caused by an external stimulus, how can we ever be absolutely certain in any given moment that what we are perceiving is real and not a hallucination? This leads to the philosophical argument from hallucination, a classic skeptical challenge. It goes like this. 1. It is possible for a person to have a perceptual experience, e.g., seeing a dagger, that is subjectively indistinguishable from a veridical perception, but where there is no corresponding external object. 2. If such an indistinguishable experience is possible, then we do not have direct, unmediated access to the external world itself, but only to our own internal mental representations. 3. Therefore, we cannot be certain that our ordinary perceptions are veridical and not just elaborate hallucinations. While we typically assume our perceptions are reliable, the mere possibility of undetectable hallucination introduces a permanent sliver of doubt about our connection to an external reality. Modern neuroscience attempts to understand the biological basis of hallucinations. Different types of hallucinations are often linked to abnormal activity in specific brain regions. Auditory hallucinations, such as hearing voices, common in schizophrenia, are often associated with spontaneous activity in the auditory cortex, the same brain region that processes real sounds. The brain misinterprets this internal neural noise as an external voice. This is sometimes framed as a failure of source monitoring, the ability to distinguish between internally generated thoughts and externally generated perceptions. Visual hallucinations are linked to activity in the visual cortex. The intricate geometric patterns often seen at the onset of a psychedelic experience, for instance, are thought to correspond to the inherent structure and firing patterns of neurons in the early visual processing areas. The more complex hallucinations of objects or beings likely involve the activation of higher-level association cortices, where memory, emotion, and perceptual templates are stored. Perception distortion similarly reveals the constructive process. Conditions like Alice in Wonderland syndrome, which can be associated with migraines or certain viral infections, involve profound distortions of perceived size and space. A person might perceive objects as suddenly shrinking, micropsia, or enlarging, macropsia, or feel that their own body parts are changing size. This suggests a disruption in the brain's size constancy mechanisms, the unconscious calculations that normally keep our perceived world stable. It reveals that the stability of perceived size and shape is not a given, but an active computation that can be disrupted. The mindfuck of these phenomena lies in their demonstration of the brain's autonomy in creating experience. They show that the reality your brain creates is not merely a passive response to the world, but can be a powerful, self-generated production. The theater of the mind has its own scriptwriters, directors, and special effects crew, and sometimes they put on a show without any input from the outside world. This radically undermines our intuitive sense of being a direct observer of a stable, external reality. It suggests our brain is a simulation engine, constantly generating a model of the world. Most of the time, that model is tightly constrained and corrected by sensory data. This is normal perception. In a hallucination, the simulation engine is running free, generating content based on internal states, memory fragments, and random neural noise. Understanding hallucinations and perception distortion is not just about understanding pathology, it's about understanding the fundamental nature of perception itself. These errors in the system reveal its underlying mechanisms, just as optical illusions do. They show us the immense creative power of the brain and the fragility of our consensus reality. They also foster empathy, helping us understand the often terrifying and confusing subjective experience of individuals with mental illnesses that involve hallucinations like schizophrenia. Their experience is not less real to them. Their brain is simply constructing a different reality. As you continue to relax deeply, contemplate the creative power of your own mind. Acknowledge that the same neural machinery that constructs your waking world also constructs your dreams each night, a world that feels completely real while you are in it. Recognize that the stability and coherence of your everyday perception is a remarkable achievement, a careful balancing act between external data and internal construction. The possibility of hallucination is the shadow cast by the brain's creative light. Let this understanding dissolve any rigid attachment to a single, objective reality. Find peace in the dynamic, generative nature of your own consciousness. Knowing that your brain is a master storyteller, constantly weaving the tapestry of your experienced world. Resting calmly within the profound mystery of its own creative power as you fall asleep. Time perception. Let us now turn our attention to one of the most fundamental yet elusive dimensions of our existence: time. We are immersed in it, our lives are defined by its passage from past to future, our actions paced by its rhythm. But how do we actually perceive time? Unlike sight or hearing, we have no dedicated sensory organ for time. We cannot see it, touch it, or taste it. Yet, we possess a rich and complex subjective experience of its duration, its sequence, and its seemingly relentless forward flow. The mechanisms by which the brain creates this experience, how it constructs our sense of a moment, a minute, a lifetime, represent a profound psychology mystery. Our internal clock is a fickle and malleable thing, capable of speeding up, slowing down, and being warped by emotion, attention, and memory. The perception of time is a deep secret of perception, questioning whether the steady, objective, clock time of physics bears any resemblance to the fluid, subjective, mind time that constitutes our lived reality, inviting deep relaxation through contemplating the strange, elastic nature of temporal experience as you fall asleep. One of the central mysteries is how the brain keeps track of duration. How do you know the difference between a 5-second pause and a 30-second one? The dominant theory suggests that the brain has an internal pacemaker accumulator model. It proposes a kind of internal pacemaker that emits regular neural pulses like the ticking of a clock. When we need to time an event, a cognitive gate opens and an accumulator starts counting these pulses. The more pulses accumulated, the longer the perceived duration. This model suggests that our perception of time can be altered by anything that affects the speed of the internal pacemaker or the way the gate operates. For example, our emotional state dramatically warps our time perception. Fear is a powerful time dilator. During moments of intense threat, a near miss in a car, a sudden fall, many people report that time seems to slow down dramatically, allowing them to perceive events in vivid, slow motion. One theory for this is that fear and high arousal cause the brain's internal pacemaker to speed up, emitting more pulses in the same objective interval. The accumulator therefore collects more ticks, and the brain interprets this larger count as a longer duration. This is highly adaptive. Slowing down perceived time during a crisis could afford us more apparent time to process information and react. Conversely, when we are bored or disengaged, time can seem to drag on interminably, perhaps because our pacemaker slows or our attention to the passage of time increases. When we are deeply engaged and in a state of flow, time seems to fly by, possibly because our attentional resources are so focused on the task at hand that the gate to the time accumulator is neglected, and fewer ticks are registered. Attention itself is a key modulator. The more attention we pay to the passage of time itself, the slower it seems to go. This is because attending to time may increase the resources dedicated to counting the pacemaker's pulses. If you are waiting for a pot to boil and watching the clock, every second feels elongated. If you are engrossed in a fascinating conversation, an hour can disappear in what feels like minutes. The saying, "a watched pot never boils," is a piece of folk wisdom capturing this deep perceptual truth. The role of the body in time perception is another layer of the mystery, connecting to the idea of embodied perception. Our internal biological rhythms, our heartbeat, our breathing, our metabolic rate, may serve as unconscious pacemakers or reference points for our sense of duration. Changes in our physiological state, such as those induced by stimulants, which can make time feel faster, or depressants, which can make it feel slower, directly impact our internal clock. The experience of time is not a disembodied mental calculation. It is deeply grounded in the rhythms of our biological existence. Another profound puzzle is how the brain constructs the present moment. What we experience as now is not an infinitesimal point in time, but a brief window of temporal integration, sometimes called the specious present. It is the duration over which our brain binds together sensory information into a single, coherent experience. Without this, we would perceive only a chaotic flicker of disconnected sensations. But how long is this window? And how does the brain create this feeling of a moving yet temporally extended now? This brings us back to the binding problem but applied to time. It's a mind fuck to realize that the present moment you are experiencing is not an instant, but a construction, a brief story your brain is telling itself about what is happening right now, stitched together from information that has already passed. Our perception of longer timescales is heavily influenced by memory. Our sense of the past week, month, or year is not a linear recording but a narrative reconstruction based on the number and salience of the memories we formed during that period. This leads to another paradox. Why does time seem to speed up as we get older? One theory suggests it's a matter of proportion. For a 10-year-old, 1 year is a tenth of their entire life, a huge proportion. For a 50-year-old, 1 year is a 50th of their life, a much smaller relative chunk, so it feels as though it passes more quickly. Another theory focuses on novelty. Childhood and youth are filled with new experiences, which create many distinct, strong memories. The brain uses the density of these memories as a cue for duration. A period rich with novel memories feels longer in retrospect. As we age, life can become more routine, leading to fewer distinct memories being formed per year. The years then seem to blur together and feel shorter when we look back. The subjective length of our past is a story written by memory. The nature of time perception is a deep psychology mystery because it reveals that our experience of time's flow, duration, and even the present moment is not a direct perception of an objective reality, but a complex and malleable construction. The reality your brain creates is one with a fluid, subjective temporality. It questions the very idea of a single objective time, and suggests we each inhabit our own unique temporal world, shaped by our attention, emotions, memories, and physiology. As you continue to relax deeply, bring a gentle awareness to your own sense of time's flow. Feel the rhythm of this present moment, this specious present your brain is constructing for you. Recall a memory of a time that seemed to fly by, and a time that seemed to drag on. Acknowledge that your internal clock is a fluid, personal, and mysterious thing. Let go of the rigid idea of clock time as the only reality. Find peace in the subjective, elastic nature of your own temporal experience. Appreciate the secret that your brain is not just a passenger in time, but the very composer of its rhythm. Resting calmly, adrift in the gentle, flowing, and ever-shifting river of your own perceived time as you fall asleep. Depth perception cues. The world we experience feels undeniably three-dimensional. We perceive a rich landscape of objects near and far, of space receding into the distance, of solid forms possessing volume and depth. Yet, the raw data our brain receives from our eyes is fundamentally two-dimensional. The retina at the back of the eye is a flat surface like a tiny movie screen. So how does the brain perform the incredible magic trick of transforming a pair of flat 2D images into the immersive 3D reality we inhabit? This remarkable feat is achieved through the interpretation of a wide array of depth perception cues. These cues are the subtle clues and assumptions that our visual system uses to infer distance and construct a three-dimensional model of the world. Understanding these cues reveals a profound secret of perception, that our experience of depth is not a direct perception, but a brilliant, unconscious inference, a best guess based on interpreting these various signals. The seamlessness of this construction is a psychology mystery that highlights the incredible computational power of the brain, inviting deep relaxation through contemplating the hidden geometry of vision as you fall asleep. The cues our brain uses can be divided into two main categories: binocular cues, which rely on the use of both eyes, and monocular cues, which can be perceived with just one eye. Let's first consider the binocular cues, which provide us with our most powerful sense of stereoscopic depth. The primary binocular cue is retinal disparity, or stereopsis. Because our two eyes are separated by a few inches, they each view the world from a slightly different angle, capturing two slightly different images. You can see this by holding a finger up in front of you and looking at it first with one eye closed, then the other. The finger will appear to shift its position relative to the background. Your brain receives these two disparate images and, in a remarkable computational feat, fuses them together into a single unified percept. The degree of difference, or disparity, between the two images provides precise information about the relative distance of objects. Objects that are closer to you will have a larger disparity between the two retinal images, while objects far in the distance will have a very small, almost negligible disparity. This process is what creates the rich, immersive feeling of 3D vision, the sense of objects popping out in space. It is the basis for 3D movies and virtual reality headsets, which work by presenting a slightly different image to each eye to simulate natural retinal disparity. Another binocular cue is convergence. As you focus on an object that is moving closer to you, your eyes must pivot inward or converge to keep it in focus. The brain registers the degree of muscle tension required to converge the eyes, and it uses this feedback as a cue for distance. A high degree of convergence means the object is very close. Parallel lines of sight mean the object is very far away. This cue is most effective for objects that are relatively near to us. While binocular cues are powerful, we are not lost in a flat world if we close one eye. This is because the brain is also a master at using a whole suite of monocular cues, which are often called pictorial cues because they are the same tricks that artists use to create the illusion of depth on a flat canvas. One of the most important is linear perspective, the tendency for parallel lines like railway tracks or the sides of a road to appear to converge as they recede into the distance. Our brain has learned that converging lines signal depth. Related to this is texture gradient. A textured surface, like a cobblestone street or a field of grass, appears coarser and more detailed up close, and finer and less detailed as it recedes into the distance. This change in texture provides a powerful cue for distance. Interposition or occlusion is another simple yet effective cue. When one object partially blocks the view of another object, our brain assumes that the blocked object is further away. Relative size also plays a key role. If we see two objects that we know to be roughly the same size, like two people, the one that casts a smaller image on our retina is perceived as being further away. Artists use this constantly, painting distant figures smaller to create a sense of depth. Relative height is another cue. Objects that are higher in our visual field are often perceived as being more distant, especially for objects on the ground plane. Light and shadow provide crucial information about the three-dimensional shape and position of objects. The way light falls on an object, creating highlights and casting shadows, gives our brain clues about its form, curvature, and location relative to other objects in the light source. Our brain typically assumes a single light source coming from above, an assumption that can be exploited by illusions. Finally, atmospheric perspective tells us that objects in the far distance tend to appear hazier, less sharp, and slightly bluer than closer objects, due to the scattering of light by particles in the atmosphere. This cue helps us judge the distance of faraway mountains or landscapes. The psychology mystery lies in how the brain takes all of these disparate, sometimes conflicting cues and seamlessly, instantly, and unconsciously integrates them into a single, stable, and coherent perception of three-dimensional space. It is a process of massive parallel computation and statistical inference. The brain is constantly weighing the evidence from each cue to construct its best guess about the layout of the world. It is this inferential process that makes us susceptible to certain illusions like the Ames room, which cleverly manipulates perspective cues to override our size constancy. This understanding profoundly questions our naive realist view of the world. We don't see depth directly. Depth is not a property of the 2D image on our retina. It is a conclusion, a calculation, a property of the 3D model that our brain creates. The immersive spatial reality we experience is a masterful construction, a virtual reality simulation generated by our own neural hardware based on interpreting these subtle cues. As you continue to relax deeply, become aware of the sense of space in the room around you even with your eyes closed. A sense of near and far. Acknowledge that this feeling of depth is a remarkable creation of your mind, built from a host of subtle cues. Contemplate the magic of retinal disparity, the logic of linear perspective, the information held in a shadow. Appreciate the silent, incredible computational work your brain is doing right now to build this 3D world for you. Let go of the idea that you are simply looking out into space. Instead, find peace in the understanding that you are living within a rich, spatial reality skillfully constructed by your own perception. A secret it keeps so well that the world feels undeniably, effortlessly three-dimensional, resting calmly within the deep, silent architecture of your own visual world. Motion perception. Our world is not static. It is a world in constant motion. We perceive the gentle drift of clouds, the swift flight of a bird, the subtle gesture of a friend's hand, the rush of passing scenery. The perception of movement is so fundamental to our survival and interaction with the world that we often take it for granted. But how does the brain achieve this? How does it transform a series of static snapshots on our retinas into the smooth, continuous experience of flow and movement? The mechanisms of motion perception represent another deep secret of perception, revealing that our experience of motion is not a direct registration of an object's displacement, but an active and sometimes fallible construction of the brain. Phenomena like apparent motion show how the brain can create movement where there is none, while the rare condition of motion blindness reveals the catastrophic consequences when this constructive process fails. This psychology mystery questions the very fabric of our temporal experience, showing how the reality your brain creates is not just spatial, but dynamically animated through complex neural computations, inviting deep relaxation as you contemplate the silent engine of motion in your mind as you fall asleep. Let's begin by considering the challenge. As your eyes scan a scene or as an object moves across your visual field, the image projected onto your retina is constantly changing. The brain's task is to distinguish between changes caused by your own movements, eye, head, and body movements, and changes caused by the actual movement of external objects. It must solve this complex problem instantly and unconsciously to present you with a stable world containing moving objects. It does this through a sophisticated system involving specialized neurons in the visual cortex, particularly in an area called MT or V5, that are selectively tuned to detect motion in specific directions and at specific speeds. These neurons act as the brain's motion detectors. However, the brain doesn't just detect motion, it actively constructs it. This is most powerfully demonstrated by the phenomenon of apparent motion. This is the illusion of movement that arises when static images are presented in rapid succession at slightly different locations. This is the fundamental principle behind all movies, animations, and digital displays. A film is just a series of still photographs, typically 24 per second. When they are projected rapidly, our brain does not perceive a flicker of static images. It perceives smooth, continuous motion. The brain fills in the gaps between the frames, creating the experience of movement where, objectively, there is only a sequence of still states. This illusion, sometimes called the phi phenomenon, reveals that our perception of motion is not a direct detection of an object's continuous path, but an inference, a best guess the brain makes to explain the rapid change in the visual input. The most logical explanation for one object disappearing and a similar one appearing nearby is that the object moved. So, that is what the brain shows us. This constructive process can be even more subtle. The beta movement illusion can occur with just two stimuli. If a light flashes on in one position, and then flashes off as another light flashes on nearby, we perceive a single light moving from the first position to the second. Our brain creates a trajectory and a sense of passage through the intervening space, even though nothing physically traversed it. This creative, inferential nature of motion perception is a constant, background process that animates our entire visual world. It is so effective that we mistake the constructed experience for a direct registration of reality. The profound necessity of this system is tragically revealed by the rare neurological condition known as akinetopsia, or motion blindness. Individuals with damage to the motion processing areas of their brain, like area V5, lose the ability to perceive smooth motion. Their world becomes a disjointed series of static snapshots, like viewing reality under a strobe light. They can see objects when they are still but cannot perceive their movement. Pouring a cup of tea is a nightmare, as the liquid appears frozen in one position and then suddenly, inexplicably, overflowing on the table. A moving car might appear in one location, then another without any sense of the movement between those 2 points. Crossing a street becomes a life-threatening ordeal. The experience of people with motion blindness is a stark and terrifying reminder that the smooth, flowing cinematic reality we all experience is not a given. It is a delicate and precious construction of a healthy brain. Their condition is a psychology mystery that acts as a negative image, revealing the essential nature of the perceptual process we all take for granted. The mindfuck of motion perception is realizing that the continuous flow of movement you experience is an elaborate interpolation, a story your brain tells itself between static frames of sensory data. Your conscious experience of motion is a smoothed-out, user-friendly summary of a far more complex and fragmented underlying process. This questions the very nature of temporal continuity in our perception. Is the flow of motion real, or is it a conceptual gloss on a series of discrete nows? This mystery connects to other puzzles we've explored. Zeno's arrow paradox, which questioned how an arrow can move if at any instant it is still, is conceptually resolved by the brain's motion perception system. The brain doesn't perceive a series of still instants. It integrates information over time to directly compute motion vectors. It is fundamentally built to perceive flow, not just static states. The brain's solution to Zeno's paradox is to not play his game. It refuses to see the world as a collection of frozen moments. Understanding the constructive nature of motion perception can also change how we see art and media. The animator, the filmmaker, the user interface designer, they are all, in a sense, practical psychologists, exploiting the principles of apparent motion to create compelling illusions of movement and life from static elements. They are tapping directly into the secret, creative processes of the brain. As you continue to relax deeply, become aware of the subtle sensations of movement within and around you, the gentle rise and fall of your breath, the slow drift of a thought through your mind. Contemplate the idea that this experience of flow, of smooth transition, is a masterpiece of your brain's creation. An illusion woven from discrete moments, a story told between the frames. Acknowledge the silent, ceaseless work of the motion-detecting neurons in your brain, tirelessly creating a dynamic, animated reality for you. Let go of the notion of seeing movement directly, and instead find a sense of wonder in the perceptual magic that makes it possible. Find peace in the smooth, continuous flow of your constructed experience, a testament to the elegant solutions your brain has evolved to make sense of a changing world. Resting calmly, adrift in the gentle, flowing river of your own perception as you fall asleep. The brain is a prediction machine. We have explored many individual secrets of perception, how our brain handles illusions, ambiguity, motion, and color. Let us now zoom out to consider a powerful, overarching theory that attempts to unify many of these phenomena into a single, elegant framework. This is the theory of the brain as a prediction machine, often discussed under the name predictive coding or predictive processing. This theory proposes a radical shift in our understanding of perception. Instead of viewing the brain as a passive device that primarily reacts to sensory information coming in from the outside world, a bottom-up process, it suggests the brain is an active, constantly working prediction engine. It is always generating a model, a hypothesis, about the causes of its sensory input. Perception, in this view, is not the process of building a model from scratch based on incoming data. It is the process of updating the brain's ongoing predictions using sensory data to correct prediction errors. This is a profound mindfuck that completely inverts the traditional view of perception. You don't just see what's out there. You see what your brain expects to see, lightly corrected by reality. This psychology mystery questions the very direction of information flow in the mind and suggests that the reality your brain creates is a controlled hallucination, constantly being disciplined by the senses. Let's unpack this revolutionary idea. The traditional view sees perception as a hierarchical, bottom-up process. Light hits the retina, this signal is processed into lines and edges in the early visual cortex, which are then assembled into shapes, which are then recognized as objects in higher cortical areas. Information flows from the senses up to the mind. The predictive coding model flips this on its head. It proposes that the primary flow of information is top-down. Higher levels of the brain, based on prior knowledge and experience, are constantly generating predictions about what the lower levels should be experiencing. For example, your brain, knowing you are in your bedroom, predicts the presence of a bed, a lamp, a window. These predictions flow down the perceptual hierarchy. The role of the senses, then, is not to transmit a full, detailed picture of the world upwards. Instead, their primary role is to transmit the prediction error, the mismatch between the brain's prediction and the actual sensory input. If the sensory input from the eyes perfectly matches the brain's prediction of bed, then very little information needs to flow upwards. The prediction is confirmed, and the error signal is low. You perceive the bed. However, if there is something unexpected, a cat sleeping on the bed that wasn't in your model, the incoming sensory data will not match the prediction. This generates a strong prediction error signal that flows up the hierarchy. This error signal then forces the higher levels to update their model of the world. The brain revises its hypothesis from bed to bed with a cat on it. The conscious perception we experience is the result of this updated, corrected model. In this framework, perception is the process of minimizing prediction error. The brain is constantly trying to create a model of the world that accurately predicts its sensory inputs, thereby reducing surprise and allowing it to navigate efficiently. What we perceive is not the raw sensory data itself, but the brain's current best hypothesis about what is causing that data. This theory elegantly explains many of the secrets of perception we've discussed. Optical illusions can be seen as situations where the brain's prior predictions are so strong that they override the bottom-up error signals, causing us to perceive what the brain expects to see, even if it conflicts with the raw data. Top-down processing and the role of expectation are no longer just features of perception. They are its central operating principle. The brain's filling in of the blind spot is a perfect example. With no sensory data coming in, there is no error signal to correct the brain's prediction that the surrounding pattern continues, so that is what you perceive. Hallucinations in this model can be understood as a state where the top-down predictions are too strong, or the bottom-up error signals are too weak, causing the brain to perceive its own internally generated model as external reality, untethered from sensory input. The mind fuck of the predictive coding model is profound. It suggests that your waking conscious experience has more in common with a dream or a controlled hallucination than with a direct perception of the external world. Your brain is not a window, it is a simulation engine. It generates an entire virtual reality of what it expects the world to be like, and then uses your senses merely to fine-tune that simulation and keep it tethered to the real world. The feeling of reality is the feeling of a successful low-error prediction. Surprise is the feeling of a failed prediction that requires a model update. This psychology mystery lies in understanding the precise neurobiological mechanisms that implement this predictive coding scheme. How are these predictions generated and represented in neural activity? How are error signals calculated and propagated through the cortical hierarchy? While there is growing evidence for predictive coding-like mechanisms in the brain, a complete picture is still emerging. Furthermore, the theory has deep philosophical implications. It questions the distinction between perception and belief. If perception is just the brain's best hypothesis, it becomes much more like a belief about the world, constantly being updated by evidence. It also offers a potential framework for unifying many different brain functions, perception, action, learning, attention, under a single principle of prediction error minimization. Action, in this view, is not just a response to perception. It is a way of changing the world to make our sensory input match our predictions. E.g., if I predict my hand is holding a cup, I move my hand until the sensory feedback matches that prediction. Understanding your brain as a prediction machine can be a source of deep insight and calm. It explains why we are so comfortable with the familiar and sometimes unsettled by novelty. The familiar is easy to predict, requiring little cognitive effort, while novelty generates large prediction errors that demand mental resources to update our model. It explains why our beliefs and expectations have such a powerful influence on our experience. As you continue to relax deeply, contemplate your brain not as a passive receiver, but as an active, tireless predictor, constantly dreaming up a model of reality and using your senses to check its work. Feel your perception of this moment not as a raw signal from the outside, but as a refined hypothesis, a coherent story your brain is telling itself right now, a story that has successfully minimized prediction error. Let go of the idea of a clear division between what is out there and what is in here. Find peace in the understanding that you are living within a controlled, self-correcting hallucination, a beautiful, functional simulation that your brain creates to make sense of the profound mystery of existence. Resting calmly, trusting in the incredible predictive power of your own mind as you fall asleep. Sensory adaptation. Let us now turn our attention to a pervasive, yet often unnoticed, secret of perception that governs our relationship with the world around us. Sensory adaptation. This is the fundamental process by which our sensory neurons become less responsive to constant, unchanging stimulation over time. Think about the feeling of putting on a watch or a ring. You notice its pressure for a few moments and then the sensation simply fades from your awareness. Or consider walking into a room with a distinct smell. It's powerful at first, but within minutes you no longer notice it. This getting used to stimuli is not a failure of our senses, but a crucial feature of their design. Sensory adaptation is a deep psychology mystery that reveals how our brain creates reality by prioritizing change over constancy. It questions our ability to perceive the world objectively, showing that our perceptual baseline is constantly shifting and recalibrating, a process that invites deep relaxation through acknowledging the mind's focus on the new and its graceful letting go of the old as you fall asleep. The mechanism of sensory adaptation occurs at multiple levels of the nervous system, starting right at the sensory receptors themselves. When a receptor cell, like a touch receptor in your skin or a photoreceptor in your eye, is exposed to a constant, unchanging stimulus, it gradually reduces its firing rate. It essentially tells the brain, This stimulus is still here, but it's old news, it's not changing, so it's probably not important. The brain, in turn, pays less attention to this steady, predictable signal. This process is incredibly efficient. It allows our perceptual systems to filter out the overwhelming amount of constant, irrelevant background information so that we can remain highly sensitive to what truly matters for survival and interaction: change, novelty, and potential threats or opportunities. Imagine if you never adapted. You would be perpetually aware of the pressure of your clothes on your skin, the hum of the refrigerator, the feeling of the chair beneath you, the specific scent of your own home. Your conscious awareness would be flooded with a constant barrage of unchanging information, making it incredibly difficult to detect new and potentially important stimuli. Sensory adaptation is the brain's way of defining normal and then ignoring it, so that it can focus its limited attentional resources on deviations from that norm. It is the secret to how we can sit comfortably in a room without being constantly distracted by the feeling of the air temperature, only to immediately notice a sudden, cool draft. This principle operates across all our senses. In vision, if you manage to perfectly stabilize an image on your retina so that it doesn't move at all, which is difficult because our eyes are always making tiny, involuntary movements called microsaccades, the image will actually fade from your perception and disappear into a uniform gray field. The photoreceptors adapt to the constant input and stop firing, and the brain, receiving no new information, perceives nothing. The tiny, constant movements of our eyes are essential to prevent this, constantly refreshing the input to the receptors and keeping the world visible. This is a profound insight. Even our perception of a static, unchanging world requires constant subtle motion to overcome adaptation. In hearing, we adapt to a constant background noise, like the drone of an airplane engine or the hum of traffic, allowing us to better detect a new sound like a voice speaking to us. In touch, as mentioned, the pressure of a watch or glasses becomes unnoticeable. In smell, adaptation is particularly rapid and profound, preventing us from being overwhelmed by our own body odor or the constant scent of our environment, while keeping us sensitive to new smells that might signal food, danger, like smoke, or a potential mate. Even our sense of taste adapts. The first bite of a sweet dessert is often the most intense, with the perceived sweetness diminishing with subsequent bites. The psychology mystery of sensory adaptation lies not just in its efficiency, but in what it reveals about the reality your brain creates. It demonstrates, once again, that we do not have direct access to the raw, objective physical world. Our perception is not a mirror of physical stimuli, but a highly filtered and prioritized representation focused on change. The world we experience is a world of differences, not absolute values. We are built to notice the note that changes in a chord, the object that moves in a scene, the temperature that drops. The constant, unchanging aspects of reality are effectively erased from our conscious experience. This questions the very stability of our perception. The normal we experience is a constantly shifting baseline, a product of what our brain has decided to tune out. Furthermore, this principle extends beyond low-level sensory processing into higher-level cognition, a phenomenon sometimes called hedonic adaptation, which we touched upon in the paradox of hedonism. We adapt not just to sensory stimuli but also to life circumstances. The initial joy of a major positive event, like winning the lottery or getting a promotion, tends to fade over time as we adapt to the new reality. Similarly, the initial distress of many negative events also tends to lessen as we adapt. Our emotional systems, like our sensory systems, seem designed to react to changes in our well-being rather than its absolute level, always returning to a relatively stable baseline. Understanding sensory adaptation can be a powerful tool for mindfulness and appreciation. By consciously directing our attention, we can temporarily override the adaptation process and rediscover the richness of everyday sensations. You can choose to feel the texture of your clothes, to notice the specific quality of the ambient light, to truly taste your food. This act of mindful attention brings the background back into the foreground, refreshing our perception and grounding us in the present moment. It allows us to appreciate the subtle details of our existence that our brain's efficiency filters normally hide from us. As you continue to relax deeply, become aware of the constant sensory inputs your brain is currently filtering out for you. The subtle pressure where your head meets the pillow, the gentle, rhythmic sound of your own breathing, the ambient temperature of the room. These sensations have been there all along, but your brain, through sensory adaptation, has gracefully allowed them to fade from your conscious awareness to create a space of calm. Acknowledge this silent, efficient process not as a loss of information, but as a gift of peace, a fundamental secret of perception that allows for focus and tranquility. Find comfort in your brain's ability to get used to the world, to create a stable, predictable baseline from which you can rest. Letting go just as your senses let go of the constant, and drifting peacefully into the quiet novelty of sleep. The limits of perception. Throughout our journey tonight, we have explored the intricate and often surprising ways our brain creates reality based on the information it receives. We've seen how it constructs, interprets, and sometimes even deceives. For our final exploration, let us turn our attention not to what we do perceive, but to the vast, silent ocean of reality that we don't perceive at all. This is the mystery of the limits of perception. Our senses, as remarkable as they are not wide-open windows onto the totality of existence. They are narrow, specialized keyholes, providing us with only a tiny sliver of information about the physical world. The vast majority of reality is utterly imperceptible to our biological hardware. Contemplating what we can't see, hear, or sense is a profound exercise in humility, questioning our place in the cosmos and revealing that the familiar world of our subjective experience is but a small, illuminated island in an immense ocean of the unseen. This final realization can be a source of ultimate deep relaxation, a letting go of the need to grasp everything as you prepare for sleep. Consider your sense of sight. Feels so rich and comprehensive. Yet, the light we perceive as the visible spectrum, the familiar rainbow of colors from red to violet, is an infinitesimally small fraction of the entire electromagnetic spectrum. We are completely blind to the radio waves that carry broadcast through our bodies, the microwaves that heat our food, the infrared radiation that radiates from warm objects, the ultraviolet light that can burn our skin, the X-rays used in medicine, and the gamma rays from cosmic events. Other creatures on this planet perceive some of these. Bees can see in the ultraviolet, allowing them to navigate by patterns on flowers invisible to us. Pit vipers can see in the infrared, detecting the heat signature of their prey in total darkness. The reality we see is a radically impoverished version of the full electromagnetic world, tuned only to the narrow band of frequencies most useful for a diurnal primate's survival. Now, consider your sense of hearing. Humans can typically hear sound frequencies between about 20 Hz and 20,000 Hz. We are deaf to the low-frequency infrasound that elephants and whales use to communicate over vast distances, sounds that can travel through the ground itself. We are equally deaf to the high-frequency ultrasound that bats and dolphins use for echolocation, navigating their worlds with a richness of sonic detail we can barely imagine. The quiet room you are in right now is likely filled with a cacophony of sounds, both too low and too high for your ears to register. The auditory reality you perceive is a carefully filtered, species-specific slice of the full acoustic environment. Our sense of smell, while useful, is feeble compared to that of many other animals. A dog's sense of smell is estimated to be tens of thousands, or even millions of times more sensitive than our own. They inhabit a rich, complex world of aromas that is completely beyond our perceptual grasp. They can smell fear, disease, and the history of who has passed by a single spot hours earlier. We walk through this same world, largely oblivious to the immense amount of information encoded in scents, perceiving only the strongest and most biologically relevant odors. Beyond these sensory limitations, there are entire physical phenomena for which we have no dedicated senses at all. We cannot directly perceive magnetic fields, yet birds and sea turtles use them to navigate the globe with incredible precision. We have no sense for atmospheric pressure changes, which many animals can detect. We are blind and deaf to the constant shower of subatomic particles like neutrinos that are passing through our bodies by the trillion every second, having traveled from the sun or distant galaxies. These are not just trivial omissions. They are fundamental limits that define the boundaries of our experiential world. The reality your brain creates is constructed entirely from the limited data that makes it through these narrow sensory keyholes. It's like trying to understand an entire, bustling city by looking through a single window. You see a part of the reality, and your brain does a masterful job of constructing a coherent story based on that part, but it is by no means the whole story. This leads to a profound philosophical mindfuck. We are building our entire understanding of existence, our science, our philosophy, our common sense, based on an incredibly filtered, biased, and incomplete data set. We are like prisoners in Plato's cave, mistaking the shadows on our sensory wall for the full reality of the world outside. The secret of perception is not just in how the brain constructs reality, but also in how much reality it necessarily leaves out of the construction. This realization profoundly questions our anthropocentric view of the world. The way we perceive reality is not the way reality is. It is simply the human way of perceiving it, a species-specific user interface. An alien intelligence with completely different sensory organs might perceive a reality so different from ours as to be mutually incomprehensible. It might perceive radio waves as colors, magnetic fields as textures, or dimensions we cannot even conceive of. This possibility shatters the idea that our perception provides a privileged or objective account of the universe. Contemplating the limits of perception is not a cause for despair over what we are missing, but rather a catalyst for profound humility and wonder. It opens up the mind to the sheer vastness of the unknown. It reminds us that reality is always infinitely richer and more complex than our experience of it. It encourages us to appreciate our scientific instruments, radio telescopes, electron microscopes, particle detectors, as prosthetic senses, tools that allow us to peek through other keyholes and glimpse the aspects of reality that lie beyond our biological limits. As you reach the final moments before sleep, let your awareness of your own sensory world expand to include the awareness of what it excludes. Picture the vibrant ultraviolet patterns on flowers, invisible to you. Imagine the deep, rumbling infrasound conversations of whales across oceans. Sense the silent magnetic field lines that guide birds on their migrations. Acknowledge that the reality you perceive is a small, beautifully illuminated clearing in a vast, dark forest of the unperceived. Find deep relaxation in this ultimate humility, in letting go of the need to see and know everything. Trust that the reality your brain creates for you is exactly what you need, a reality tailored for a human existence. Resting peacefully, floating calmly in the immense, mysterious, and largely imperceptible ocean of reality.